Hello students, I welcome you again on fantastic platform PhysicsWallah to learn second and even more important chapter of electrodynamics, which is electric current. Okay. So let's start learning this chapter and score few more marks in our upcoming exams. In this chapter, we will learn few microscopic new quantities like current density, drift velocity, mobility of electrons or different charge carriers. Then we will learn resistivity and conductivity of metals. Then the circuit part starts and we will learn Ohm's law, KCL and KVL. KCL and KVL are actually Kirchhoff's current law and Kirchhoff's voltage law based upon few very fundamental conservation laws of physics. Then we will study grouping of resistances and many circuits related to them, like series combination of resistances, parallel combination of resistances, mixed combination of resistances, symmetrical circuits, all in this grouping of resistances, many bridges like Wheatstone bridges, etc. Then grouping of cells also. Then obviously the most important thing in electricity is power, so we'll learn about power. And finally, few measuring instruments. Obviously measurement is also a very important part of study. So few measuring instruments like ammeter, voltmeter, potentiometer and meter bridge. Okay, so let's not waste time and begin our learning. Students, in last chapter electrostatic, you must have learned that net field inside a conductor under electrostatic equilibrium is zero. Let us see how. If we take a conductor and we put some potential difference across it, or we place it in some external electric field. Let's say E naught is some external electric field. Then what happens? Since it is a conductor, it has many free electrons available in that. So all electrons feel an external force and the electrons drift towards left end and the left end becomes negative. Okay, this is called induction, electrostatic induction, and left end becomes negative because of the force and the right end becomes positive. Induction, this type of induction creates an extra field called internal electric field inside conductor, and you can see the internal electric field opposes the external electric field, and finally eventually they both cancel each other in conductor and the net field inside conductor is zero. Okay, but what if we use a special device called cell and we use it like this? This is a cell, or we also call it battery. Connect it like this. The longer line is called positive terminal of battery and this shorter line is called negative terminal of the battery. What it does? The positive terminal of battery attracts these electrons, gives them energy and sends them back to this end. Because of this, these electrons keep moving in this direction, and this induction or this distribution of charge on the end of the conductor is not as strong as it was before insertion of battery. That is why the internal electric field is not that strong as it was in electrostatic equilibrium, and then we get some net electric field inside conductor because E out is more than E inside in this case. And electrons keep moving in this direction, and if electron keeps moving in this direction, what we get? We get a continuous flow of charge. We get a continuous flow of charge, and this flow of charge is termed as electric current. Okay, so in conductors, electric current means there is some flow of charge, means they are not in electrostatic equilibrium. So the whole idea, the central idea of this chapter is not based on electrostatic equilibrium. Remember, it is based on the some potential difference applied across conductor. There is net field inside conductor, and there is flow of charge inside conductor. Okay, so when charge flows inside conductor, okay, the net rate at which charge is flowing inside conductor is called electric current. The electric current is actually net rate of flow of charge inside conductor, and it is represented as dq by dt. dq is the charge that flows inside conductor through any cross section of conductor in time, actually dt. You can also call this current as the charge flown in unit time. The charge flown in unit time, its unit can be coulomb per second, but we also call it ampere. And you all know ampere is the fundamental unit, right? Ampere is the fundamental unit. Okay, there is some very important thing, let me tell you. If you see some question in which a stream of charges, a stream of identical charges or a beam of charged particles, every charge has q, or you can say every particle has q charge on it, and they are moving in a region. They are moving in a region, and n dot you can say is the number of charges or number of charged particles crossing some particular area in unit time or in 1 second. Okay, so if in 1 second n dot is the number of charge crossing, if you multiply n dot with the charge on each particle q, you get n dot q, and n dot q will be the total charge crossing that area unit time, in unit time. So n dot q, as it is the net charge crossing in unit time, this can be called as current through that area. Okay, so remember this fact. If there are few charges crossing some area, let's say that charges crossing some area in 1 second is n dot, and if charges have magnitude q each, then the current associated is called n dot e. That's a very important. The electric current has a sense of direction, and conventionally the direction of electric current is taken as the flow direction of positive charge. But what if negative charge is moving? So if negative charge is moving, the direction of current will be opposite to the flow direction of negative charge. Always remember, if in some conductor the electrons are moving in one direction, the current will be in opposite direction. So remember, mark this point. And yes, very important thing, current is not a vector quantity. Current is not a vector quantity, though it has a sense of direction, but it is not a vector quantity because it doesn't follow vector laws. If you have to add two currents, it acts like scalars, like 3 ampere plus 4 ampere. If these two currents superimpose, it will become 7 ampere. It will not depend upon the angle between them, etc. So they are added like scalars. Okay. There's one more thing. If you want to calculate average current, the average current in some time interval delta t is equal to the total charge crossing the cross section in time delta t divided by time delta t. Okay, so average current is delta q by delta t. And if you want to calculate the net flown charge or charge flown, then the charge flown becomes average current multiplied by time, average current multiplied by time, or if we are given the current as a function of time. So if we are given current as a function of time, the charge flown would be the integral of I dt from t1 to t2. So this will be the charge flown from the time interval or from t1 to t2, you can say. Okay, so these are few fundamentals. Let's move further. Now we will learn few microscopic quantities, and the first is current density. Okay, so actually if current is moving in a thin wire, okay, it is sufficient to know what is current. But if current is distributed in a cross section like this, current is flowing in this cross section, okay, and we observe the current is not distributed uniformly. If current is not distributed uniformly, okay, then we say that we define a new term called current density, and we say the current density is not uniform. Okay, the current density is not uniform, and current density is such a vector that if you multiply current density by area, you get current. Okay, in a raw sense, you can say if you multiply current density by area, you get current. But specifically, the dot product of J dot dA, the integral of dot product of J dot dA gives you current. Okay, I think you remember the electric flux, and it was integral E dot dA. E dot dA, remember? So this we call as flux of electric field, and it is defined as E dot dA. Can you see the similarity between the two formula? So we also say the total current is actually the flux of current density. We say current as flux of current density. Remember this point. Okay. If we have uniform current density over a cross section of a wire like this is the cross section of a wire, and we have uniform current density, means entire area has uniform current distributed on it. Then I can say the current would be, we can take this J outside, okay, and then integral dA would be total area A. So I then becomes J dot A. I think you remember A is area vector, and area vector is always perpendicular to the plane of cross section on which current is passing. Okay, so always remember, we also say the current density is current per unit cross section area. Current per unit cross section area, but current should cross it normally. The current should cross it normally. So always remember current density as current per unit cross section area. This is the exact definition of current density. Okay. Then we learn few very important quantities, and you will see there are many questions asked previously based on these quantities. So to begin this, let us take a long conductor of length L, okay, a long conductor of length L, and with the help of some battery or something, we have applied a potential difference across it. Can you see the potential difference across it? This positive and this negative sign indicates that this end is at higher potential than this end. Okay, so we have applied a potential difference, and if potential is decreasing along this length or potential is decreasing towards right, you know the direction of electric field is in the direction of decreasing potential. So we have an electric field inside conductor E. Okay, we have an electric field inside conductor E. As you know, the potential difference is integral of E dot dl. Assuming E is uniform over the cross section, over the length, electric field is uniform, I can take E outside this integration sign. Also E and the dl are in same direction, the length vector and E are in same direction. So E dot dl becomes E dl. We take E outside the integration sign and dl becomes L. So the potential difference and electric field in the conductor are related with this formula. This is the first formula we have. Okay. If we do not apply this potential difference, what does these free electrons do? They do a random kind of motion, also called Brownian motion. They go, few go this way, few go that way, few go upward, few go downward, and they move in random directions, almost in all possible directions equally. Okay, that type of motion is called Brownian motion. But when we apply a potential difference, then the free electrons start drifting gradually, slowly towards the positive potential, and they gain a very small average velocity towards positive potential. They gain a very small average velocity towards positive potential, and this average velocity is called drift velocity. Drift velocity called Vd. Remember Vd. This drift velocity is given by E. Small e is electric charge, electronic charge. The E vector is electric field divided by mass of electron and multiplied by a constant tau. The tau is called relaxation time or average time between two collisions of electron. Average time between two collisions of electrons. So remember, it is relaxation time or average time between two collisions of electron. So this is Vd. Always remember. Can you see the electrons will drift in opposite direction of electric field because force on them acts in opposite direction of electric field because they are negatively charged, obviously. So drift velocity and electric field are in opposite direction. That's why we see a negative sign here. The mobility. Mobility is defined as drift speed per unit electric field. Drift speed per unit electric field. So we have drift speed here. Bring this E vector in the denominator or the magnitude E in the denominator, and you have E tau by m. So mobility is defined as E tau by m, or fundamentally by Vd upon E. Okay, so this is mobility. Let's move a little. Then we have current density, and current density in this conductor will be NEVD. It depends upon drift speed. E is electronic charge or charge of one electron, and N is number density of free electrons. Number density of free electron means free electrons available in unit volume of the conductor. Okay, so N is number density of free electrons. Okay, number density of free electrons, and it is expressed in number of electrons per unit volume, per meter cube. You can say expressed in per meter cube. So N is actually the number of free electrons available in 1 meter cube if we talk about SI system. Okay, so always remember, as you know, J is current per unit area. Current per unit area. So J is also written as I upon area. If in the cross section we have uniform current density, then only. So it is I upon area equals to NEVD. You bring this area on the right hand side and you will have C. You will have I as NEAVD. So let's write directly as current equals to NEAVD. It's a very important relation, and you will see many problems they have asked in NEET and JEE on this formula only. Okay. Next, as you know, J equals to NEVD. Okay, and VD equals EE tau by M. Let's take magnitude only. So we get J equals to N E square tau by M times E. Okay, let's look for directions. As you know, electric field is towards right. The electrons experience a force towards left, so they move left. And if electrons move left, current is towards right. So current density is also towards right. And now you see the field and current density are in the same direction. So we can apply this vectorially, and this term called, as you can see, this term depends only upon the properties of metal, the properties of material, because number density depends upon property of material. The relaxation time, average time between two collisions of electron, depends upon properties of material. E square and M, they are universal constants, you know, because this is charge of electron, this is mass of electron. So this is a constant that depends upon material of the conductor. It is called conductivity. Remember, it is called conductivity, and this law becomes J equals to sigma E, and sigma, this symbol sigma, is called conductivity of the material. Okay, the reciprocal of sigma is called resistivity. Always remember, the reciprocal of sigma is called resistivity, and that is represented by rho. So if we replace conductivity by resistivity, we get another law as E equals to rho J, E equals to rho J. Okay, so remember, sigma is conductivity and rho is resistivity of material. They are reciprocal to each other. Sigma equals to 1 by rho. Always remember. Then, okay. This law is also called Ohm's law or microscopic form of Ohm's law, which is applicable at a point. So, if at a point we have resistivity rho, and if at that point electric field is given by E vector, the current density vector at that point will be the electric field at that point divided by resistivity. So this is applicable at a point, so it is called microscopic Ohm's law. Microscopic Ohm's law. And if we take this law again, E equals to rho J, let's take E equals rho J, just take magnitudes, replace E by, see what is E? E is V divided by L, the potential difference divided by length of the conductor, and J as I upon area. So replace E by V by L and J by E equals to V by L and J as current upon area. You have V equals to rho L divided by area times I. Okay, and this is another constant that depends upon material of the conductor, material of the wire conductor, and its dimensions also, because it depends upon length of the conductor too, and as well as cross-sectional area of the conductor too, and also on material of the conductor too. So it is again a constant related to conductor. Okay, so this is called electrical resistance. Always remember, it's a very famous quantity in this chapter, electrical resistance, and represented by R. So this law becomes V equals to I R. R is a constant. If we keep physical properties of the conductor constant, R is a constant, and this is actually Ohm's law. Ohm's law, or you can say macroscopic form of Ohm's law, which is applicable over the length of the conductor. So these are few relationships, these are few interrelationships between electrical quantities, and they give you many problems based upon this. So let's learn few of them. Okay. In this question, they are saying the resistance of a wire is R ohm. Okay. We have a wire and its resistance is R ohm. Then it is melted and it is rearranged in a bigger wire. Okay, in a bigger wire of n times its original length. Okay, and if it is melted and reformed into a bigger wire, obviously if length is increased, the wire's cross section area would decrease, because we haven't added any material, we haven't removed any material, the total material is constant. Okay, the total material is constant, or you can say the volume is constant. So if we have a longer length, we will have a thinner cross section. Okay, and the new resistance is say R dash, its new length is n times initial length. Okay, so they are asking you what is the new resistance, what is R dash. How to approach this problem? It's a very simple problem. Let me give you an idea. As you know, resistance is equal to, again I must say you something, whenever you see a problem, pause the video, attempt it yourself first, and then see the solution if you find that you are getting incorrect answer. Okay, so R equals to, as you know, rho L divided by A, right? As you can see, we are given the length is changing, but we know that area would also change, the total volume is conserved, right? So what I can do, I can multiply L in the numerator and denominator, and we will get a new formula as rho L square divided by area times L. What is area times L? It is volume. And now this is a better formula if change in length is given. Why? Because the resistivity is constant, because we haven't changed the material. Material is same, right? And volume is also conserved. Volume is also conserved, right? So if rho and V is conserved, this gives you the R depends upon L square. R depends upon L square. So what will be new resistance? R dash, rho by V, and new length. And new length is N times L. N times L is square. So you get R dash as rho by V, L square and N square. As this is the old resistance R, you get N square times R. So we have the new resistance as N square R, and the correct answer is C. Okay. So let's move to the next question. And a similar question asked in mains 19. Now they say a copper wire is stressed to make it 0.5% longer. Okay, 0.5% longer. It is stressed. If a wire is stressed again, if length is increased, obviously the area will definitely decrease because material is same. Total material or total volume is same, right? So it is a similar problem, but the only difference is in the previous question, they made a big change in length. In this time, they are making a very small change in length. Again, pause the video, attempt it yourself, and then look for solution. Okay. Let me solve it. As you know, resistance equals to rho L square by volume. As I proved this formula just one question back. But as there is a small change in resistance. So whenever you see some formula like this, means you don't see any positive or negative sign, you just see a quantity depending upon multiplication and division of other quantities. And they are saying, or they are changing it by a small amount. They are changing few quantities by a small amount. Always you have to take this approach I am telling you, right? Look. So if relationship between small changes is to be made, always take log on both sides. So we have log R equals to log rho by V. Rho and V are constants, so we are clubbing them. And then we have log of L square. So log of L square becomes 2 log L. And now differentiate it. And if you differentiate this quantity, I think you have read in chapter errors. This is differentiated like this. Log R is dr by R. This is a constant, so its derivative is 0. And we have 2 dl by L. This is fractional change in resistance. This is fractional change in length. You can see fractional change in resistance is twice of fractional change in length. If you multiply this by 100, this gives you percentage change in length. And can you see percentage change is 0.5%. So put dl by L into 100 as 0.5. So you get 2 times 0.5, you get 1%. And what is on the left side? This is the percentage change in resistance. So percentage change in resistance is 1%, and the correct answer is A, right? So it's time to move for next question. Yes, again a very simple question, and they are saying a battery is applied, okay, and this battery is sending current. This battery is sending current, and the battery is sending in a spatial resistance of non-uniform cross section. Can you see this wire's cross section is non-uniform. At the left end P, it has a bigger cross section, and at right end Q, it has a smaller cross section. So wire is gradually narrowing down. But by the conservation of charge, you see the current entering this wire will leave this wire. The same current will leave this wire because there is no path where current can leak. So current throughout is same, right? Current throughout is same. We can simply say the electric the electric current is same, so this option is wrong. Because it says electric current decreases. What about drift velocity? So for drift velocity, just try to remember some relation between current and drift velocity, and I think it will strike you. I equals to NEA VD. As over the length, the current is constant. The number density of electron is constant because material is homogeneous. The electronic charge is constant. So these three terms are constant. So what you can say? You can say the multiplication of area and VD is constant. And if multiplication of area and VD is constant, as the area decreases, area will decrease from going to Q from P, the area will decrease, and as area decreases, the VD should increase. The law is simple, area is decreasing, so VD should increase to keep the multiplication constant. So first answer is correct, the drift velocity of electrons increases. The drift velocity of electron increases from P to Q. Electric field, what about electric field? I think you remember VD, the magnitude VD equals EE by m tau. EE by m tau. E by m a universal constant, tau is the constant of material, so material is obviously homogeneous. So here from here we say if VD is increasing, VD is directly proportional to electric field. So if in this question VD is increasing, electric field must also increase. So this is also a wrong answer. So all of the above are not correct. So correct answer is A only. Okay. So that's the third question. So this question says a current of 5 ampere. A current of 5 ampere is crossing a magnesium wire of cross section area 0.04. So there is a hint that current is constant throughout the wire. Current is constant, the area is constant. So if current and area are constant, obviously the current density must be a constant. So remember, current density a constant. And if you know the current density, right? If you know the current density, so I think you remember the formula I equals to integral J dot dA. In the next line they are saying that angle between J and area vector at every point is 60 degree. So I can replace this J dot dA as integral J dA cos 60, and I think you remember cos 60 is 1 by 2. And since J is a constant, I can take J and 1 by 2 outside the integration, and we are left with only dA, and the integral of dA is area of cross section. So we are left with J multiplied by 1 by 2 multiplied by cross section area, which is 0.04, and then we have current as 5 ampere. Okay, so solve this for current density, and I think you get current density as J equals to 10 divided by 0.04, and which is 250 ampere per meter square. So this is current density, and they are asking you magnitude of electric field at point of conductor. Okay, so I think you remember the relation between current density and the electric field, and they are given resistivity of magnesium. So I think you remember, but let us see it again. Okay, the relationship between electric field and current density is electric field equals resistivity times current density. Okay, so let us multiply these two. Yes, so electric field equals rho times current density J. The value of rho is 44 times 10 to the power minus 8 and multiplied by 250. Okay, 250, and you get yes, you get almost 11 times 10 to the power minus 5 volt per meter. So this is the correct answer, and the correct answer is C, right? Next question. In this question, they have given you current passing through a uniform cross-sectional area 4 times 10 to the power minus 6 meter square. The density of the aluminum conductor, actually they are given you density, and finally they are asking you the drift speed of the electrons. So let us remind the relation between current and drift velocity or drift speed. I think you remember I equals to NEA VD. So first I'll suggest solve it yourself and then look for solution. You are given current, you are given area, you are been asked the drift speed, the electronic charge we all remember. The main important thing is how to find N, the number density of free electrons. So for this number density of free electron, they are saying the density of conductor is 2.7 gram per cc. Okay, and consider every atom is donating one free electron. Consider every atom is donating one free electron. So you can assume the number density of atoms in a unit volume is same as number density of free electrons in that volume. Okay, so I'll try to find out how many atoms are there in a unit volume, and then it will be equal to number density of free electrons. Okay, so as we know, the density of aluminum is 2.7 gram per cc. This can be converted into SI units, and it will be 2700 kilogram per meter cube, or 2700 times 1000 grams per meter cube. This is the mass of aluminum in grams per meter cube. If I divide this by molecular weight of aluminum, which is 27, we get number of moles. We get number of moles in aluminum. Okay, and if we get number of moles and multiplied by Avogadro number, we get the number of atoms in unit volume, and as the question says the number of atoms is same as number density of electrons, this is actually the N we are looking for. Okay, so N becomes, Avogadro number is 6 point, or you can say it is nearly 6 times 10 to the power minus 23, but we have 5 zeros or 10 to the power 5 here, so minus 23 and 10 to the power 5 becomes 10 to the power minus 18, sorry, 10 to the power, okay, not, NV is 6 times 10 to the power 23 times 10 to the power 5. Okay, so this is the number density of electron. And now if you know number density of electron, let us find out the drift speed. According to this formula, drift speed is I divided by NEA. Okay, NEA. So drift speed becomes current, which is 10 ampere, divided by N, it is 6 times 10 to the power 28 times electronic charge as 1.6 times 10 to the power minus 19, and multiplied by the area, which is 4 times 10 to the power minus 6. And now let's do some calculations. So I think it's simple. You have 10 to the power 28, you have 10 to the power minus 19 and 10 to the power minus 6. So 19 and 6 becomes minus 25, and then we have 28. So we are left with 1000 in the denominator. So it becomes, calculate this carefully and you will get VD as 2.6 times 10 to the power minus 4. Okay, so C is the correct answer. Okay, so let's move to next question. Again, we have a very simple problem, and they say charged particles having drift velocity. They have given us drift velocity and electric field as 3 times 10 to the power minus 10 volt per meter. And they are asking the mobility. So remember the definition of mobility, and mobility equals drift velocity per unit electric field. Per unit electric field. Just divide Vd by E. So Vd is 7.5 times 10 to the power minus 4. Electric field is 3 times 10 to the power minus 10, and as an answer you will get 2.5 times 10 to the power 6. So answer is C, right? Next question. Now we have a theoretical question to answer, and in column 1 we are given some physical quantities, and in column 2 we have formula. So let's relate. The first is drift velocity. Okay. So I think that is simple, because the formula for drift velocity is E tau by m, where tau is relaxation period. Okay. So answer for A is R. Electrical resistivity, I think you all remember the E equals resistivity times current density. So resistivity is E by J. So S is the correct answer for B. Relaxation period, tau. Relaxation period is also available in this formula for drift velocity, but this has been already used up. So let us try this. Okay. Actually, I think you remember the formula for conductivity as Ne square tau by m. Conductivity we can write as reciprocal of resistivity, right? And relaxation period is tau. So keep this tau here, move this m on the left, Ne square at the bottom, and you will get relaxation period as m by Ne square rho. So answer for C is P, and D is current density, as I equals NEA Vd. Current density is I upon area, I divided by area. So obviously current density is NEVD, right? So answer for D is Q. So we have answers as RSPQ. RSPQ. The correct answer is A. Okay. So let's move to next question. Now they say the drift speed of electron. They are asking us drift speed of electron when current of 1.5 ampere is flowing in copper wire of cross section 5 mm square. The electron density is also given. What is the value of V? Okay, so I think that is a very simple problem. I equals to NEA Vd, right? NEA Vd. What is I? I is 1.5 ampere divided by N. N is 9 times 10 to the power 28. Then we have E as 1.6 times 10 to the power minus 19, and area as 5 mm square. So 5 mm square can be written as 5 times 10 to the power minus 6 meter square, and this is actually Vd. Okay. So now let us solve it. 10 to the power 28, 10 to the power 28, 10 to the power minus 19, 10 to the power minus 6, it becomes 1000, and send this 1000 in the numerator, you will get 10 to the power minus 3. Okay, so solve this carefully, and I think you will get the answer as C, right? Now we will learn about the temperature dependence of resistance. What we observe is the resistance is not constant if we heat a conductor or material. Okay, so let us learn how resistance changes with rise in temperature. So let's say theta is temperature, and if theta is increased, As resistance is rho L upon A, I can assume the length and cross section area of conductor, as conductor is a solid one, they are constant. So the main important factor is resistivity. The resistivity is actually m upon ne square tau, where mass m is the mass of electron and E is electronic charge, and they both are universal constants. But n and tau, they both are temperature sensitive. When you raise the temperature, actually you give energy to material. And when material gains energy, the electrons gain energy, and when electrons gain energy, some of the valence electrons orbiting around nucleus of atoms may get free and come into the free space of material. And when they become free, the free number of free electrons increases, so n increases. So what happens if theta is increased, n increases, right? N increases. What about tau? As you are giving energy, the electrons are gaining energy, they are moving more fast as compared to the previous case. And if they are moving fast, they will collide rapidly among each other. And if they collide rapidly, if they collide quickly, the time interval, the average time interval between two collision is going to be reduced. So always remember the fact that if theta is increased, tau decreases. As collisions are more quick, and the electrons are moving faster than before. Okay. So if we just remember this, if theta is increased, n will increase and tau will decrease. It becomes difficult for us to check the nature of resistivity because one factor is increasing and the other factor is decreasing. Actually, it depends upon material to material. Okay. So what we have observed, when we talk of insulators or semiconductors, insulators like wood, plastic, etc., and semiconductors like carbon, silicon and germanium. In these type of materials, when theta is increased, I am studying effect of rise in temperature. So when temperature is increased, what we see n increases significantly. N increases in a bigger percentage like 10%, 5%, 7%, n increases significantly. But tau decreases. But what we observe is there is a very small decrease. There is a very little decrease in tau. There is almost no change in tau. Tau decreases, but in a very small amount. Very small change. So if effect of tau is very small, I can ignore the change of tau and we can just include the change of n. So obviously if theta is increasing, temperature is increasing, n is increasing, the rho will decrease, the resistivity will decrease, and if resistivity decreases, resistance decreases, right? So resistivity or resistance decreases as temperature is raised in insulators and semiconductors, remember. But what if we have conductors? In conductors, the story is quite different. In conductors, n remains constant. When we increase temperature, n remains same. Why n remains same? Because n is already very large. N is already very large, almost maximum. N is already at its maximum value, and when you give energy to electrons, there are no electrons in valence shell. There are because almost every electron in valence shell is almost already free at room temperature. So when we increase temperature, n remains almost same or a very little change, and the n in conductors you can say remains almost same. And tau decreases. Tau. Obviously tau decreases very little, but still the only deciding factor is tau. and since tau is decreasing, the resistivity will increase, because resistivity and tau are inversely proportional to each other. So as tau is decreasing, resistivity and resistance increases as temperature of conductor increases, right? As temperature of conductor increases. So what we say in case of insulators and semiconductors, theta is raised, resistivity is decreased, and as in conductors, if theta is raised, resistances and resistivity is increased. Resistivity and resistance both increases. So what we do, we define temperature coefficient of resistance. It is a quantity that tells you how the resistance of a material changes with temperature. The temperature coefficient of resistance is defined as alpha, and alpha is applicable for both the materials, right? Alpha is actually the fractional change in resistance dr by r. It is the fractional change in resistance per unit change in temperature, means dr by r d theta. Fractional change of resistance per unit change in temperature. So remember, always remember, as here, if theta increases, rho decreases. So if theta increases, d theta is positive, but dr is negative, because rho decreasing, so r will decrease. So if d theta is positive and dr is negative, we have negative alpha for insulators and semiconductors. So insulators and semiconductors have negative thermal coefficient of expansion or negative temperature coefficient of resistance. Sorry, negative temperature coefficient of resistance. So they have negative alpha. Okay. The semiconductors and insulators have negative alpha because here as temperature is increased, rho is decreased, resistance is decreased. So d theta is positive, dr is negative. But here both are increasing. If theta increasing, r increasing, rho increasing, so I can say alpha is positive. We have positive alpha. Okay. We have positive alpha. So in case of insulators and semiconductors, what we see, when theta is increased, the resistance decreases. And in conductors, what we see, as theta is increased, resistance increases. Okay. If in some question they are saying alpha as constant, remember alpha as constant, and there is a small change in temperature, there is a small change in temperature and alpha is constant, then you can write the new temperature r dash as the old temperature r naught 1 plus alpha delta theta. This is just an approximation of this general result, right? This is an approximation of the general result, and this is valid only when alpha is constant and has a very small value, and delta theta, that is change in temperature, is also very small. Okay, then it is valid. Okay, so let us move for few questions related to this topic. The first question says the solids, which are the solids who have negative temperature coefficient of resistance? Obviously insulators and semiconductors, obviously, because you know in case of insulators and semiconductors, alpha is negative. Why alpha is negative? Because alpha is actually dr divided by r d theta, and in this case if temperature is increased, resistance decreases. So if temperature is increasing, d theta is positive, resistance decreasing, dr is negative. So we have negative upon positive, means alpha is negative. So let's move to next question. This says, which of the following graph represents variation of resistivity with temperature for copper? You know copper. Copper is a conductor. And in case of conductor, as temperature is increased, resistance increases, right? So we have two graph which matches this criteria. In A and C, as temperature is increasing, the resistivity is decreasing. They are obviously wrong. But in B and D, as temperature is increasing, the rho is increasing. But how to select between B and D? The answer is the linear relationship I told you between resistivity and theta, or resistance is in theta. The linear relationship is only valid when alpha is constant, very small, and temperature change too is very small. But otherwise, the relationship is curved one. It is not a linear relationship. Always remember, if you change the temperature by a bigger amount, the relationship is not linear, it is curved. So correct answer is D. Always remember. Okay. Then again, we have a very important concept. It's a little like you will have to remember a few things. Okay. But it is a very important, and almost every year you can see this question repeating itself, right? So this is about how to read the value of a resistance. When we go in the market and buy a resistance, okay, actually the value of resistance is not written on that piece of resistance. On that resistance, there are a few lines drawn, and the color of lines give you the value of resistance. So we say this as color code. Usually there are 4 lines. Sometimes there are 3 lines only, but usually there are 4 lines. And these lines, the color of these lines will tell you the value of resistance. Let me tell you how. Okay. Always remember, the first 2 lines will give you the 2 digits of resistance. They give you the 2 digits of the resistance, and the third line gives you the order of the resistance, like it is 10 to the power 5 or 10 to the power 3. The third gives you order. And the fourth line gives us the uncertainty, the tolerance of the resistance, the error, the possible error in the resistance. Okay. So let me tell you how to read the color codes, and for reading the color code you will have to remember this table. This is a very big table, but it says black, brown, red, orange, yellow, green, blue, violet, white, gold, silver, and no color. And they are arranged in this order: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is the order, and this is the tolerance. 5%, 10%, 20%. This is the tolerance, or you can say the uncertainty, or you can say the error. So let me tell you how to read the color codes. Okay. But first, how we will remember this? So there is a line. If you remember that line, it will be very easy for you to remember the color codes. B.B. Roy. You can say it is a name of a person, B.B. Roy, but it starts with black, brown, red, orange, yellow. Black, brown, first is black, brown, red, orange, yellow. So B.B. Roy of Great Britain, great is green, blue is, B is Britain, okay. Of Great Britain had a very good wife, violet, grey and white. Violet, grey and white. If you remember this line, it may become easy for you to remember this order: black, brown, red, orange, yellow, green, blue, violet, grey and white. Okay. Sometimes there may be a confusion, but you must remember: the first B is black, the second B is brown, and the third B is blue. Okay. When you write this, then the number associated with first is 0, then 2, then 3, 4, 5, 6, 7, 8, 9. So number starts with 0. Remember, number starts with 0. Okay. And multiplier starts with again 10 to the power 0. Actually, there was 1 written in the table, but actually the 1 is 10 to the power 0. You know, 10 to the power 0 is 1. So order is 0. So in front of B we have 10 to the power 0, then 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4, 10 to the power 5, etc. Okay. So number starts with 0 to 9. The order starts with 0 to 9. 10 to the power order. Okay. Now suppose in some question they say you this line is red, this line is black, and this line is yellow, and this line is silver. So I told you that the first two lines give you the 2 digits. Remember, the first two lines give you the 2 digits. So red and black. Let us read. Red and black. Red means 2, black means 0. So the resistance is 20. We got 2 digits of resistance. Then we have third line as yellow. Third line gives you order. Third line is yellow, and yellow is 4. So order is 4. So we have 20 times 10 to the power 4. Remember, 20 times 10 to the power 4. Okay. Then I have silver line, and if I have silver line means there is a 10% error. So tolerance is 10%. 10% error. So the value of resistance is 20 times 10 to the power 4 with an error of 10%. So that is how you read color codes of resistances. Remember, color codes of resistances. And please remember the line, B.B. Roy of Great Britain had a very good wife. Okay. The number starts with 0 up to 9. The multiplier starts with 0 up to 9. Okay. Gold and silver, sometimes they also give an order of 10 to the power minus 1 and 10 to the power minus 2, but that is very rare, I assure you. Let us solve a problem based on this. They are given a carbon resistance, and carbon resistances R equals 47 plus minus 4.7 times kilo ohm. Kilo ohm means 10 to the power 3 ohm. Okay. So if you look at this resistance, again I say solve it yourself first, then look for solution. If you look at this resistance, the first two digits are 4 and 7. 4 and 7. Let us write the sequence. B.B. Roy of Great Britain had a very good wife. It starts with 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. So 4 is yellow, 7 is violet. So we have first two lines as yellow and violet. Then we have order as 3, and order is 3 means the color of third line must be orange. And can you see the error is 10% of the value? It is 47, it is 47 by 10. So if error is 10%, the fourth line should be of a silver one. Okay, so we should have yellow, violet, orange, silver. So yellow, 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 violet, orange, silver. So correct answer is B, students. Okay, so that is a very simple question. The only thing is remember this sequence. Okay, next and very simple question again. Now they have given us resistance and the color codes. So we have yellow, violet, brown, gold. Okay, let's write. B.B. Roy of Great Britain had a very good wife. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So yellow and violet. Yellow and violet are 4 and 7. So the resistance should be 47. Order black, brown. Brown is second. The sequence starts with black. Remember, the sequence starts with black. So order is 1. So multiplied by 10 to the power 1. And silver. Okay, gold. Gold line means there is a 5% error only. So we have a 5% error. And answer is obviously 47 times 10, that is 470. 470 ohms with a 5% error. So correct answer is A. So that was a very simple question. Let's move to next question. Again, I think you all can solve it very easily. We have red, violet, orange, silver. Let us read from the previous slide. What was it? Red, violet, orange, silver. So red means 2, orange means red, violet, I think violet, red, violet. So red is 2, violet is 7. So answer should contain 27. Okay. So answer must have 27. The third line is orange. Orange means 3. Orange means 3. So order is 10 to the power 3. And silver line means 10% error. Silver line means 10% error. 10% error. So we have 27 kilo ohm with 10% error. The correct answer is D, students. Okay. Next again, I think you all can solve it very easily, but still we have, okay, there is a confusion whether this G stands for green or gray. Green or gray. Obviously this is orange, this is yellow, but what is the first term? Green or gray? If you look into this sequence, we have green as 5, gray as 8. Green as 5 and gray as 8. Okay, but if you see the options, 5 is available, 8 is not. So it must be green. Okay, it must be green. Then orange. And orange is at 3. Then we have 53. We have two numbers as 53. And then we have yellow. Let us see what is the order for yellow. For yellow we have 4. For yellow we have 4. So 10 to the power 4. And then we have a golden line. Golden line means 5% error. We have 5% error. 5% error. So this is the value of resistance and it matches with option A. So option A is the right answer. Okay. Now it is time to learn how to solve electrical circuits. This is perhaps the most interesting part of this chapter. But before we begin, let us learn the elements that we are going to see in electrical circuits. Obviously, they are batteries and resistances. So let's begin with resistance. If this is a resistance of resistance R, okay, this actually is called a resistor and its property is resistance. So resistance is say R and current is flowing from A to B. If current is flowing from A to B, you already know that the potential difference across resistance V equals to current times resistance R. Okay, so we have a potential difference developed across A and B. Okay, but I think you remember, if the current is towards right, the current density vector is towards right. And current density vector is given by conductivity times the electric field. So if current density is towards right, obviously the electric field is towards right. And we learned in electrostatics that in the direction of electric field, potential decreases. So in the direction of electric field, potential decreases. Okay, so we can say the terminal A is at higher potential and terminal B is at lower potential. Here in electrical circuits, we show higher potential by positive sign and lower potential by negative sign. Okay, so we have point A at higher potential, than point B, and difference between potentials of A and B will be I times R. Okay, so what I can write is VA minus VB. The potential difference across A and B is I times R. You can easily remember it. Just remember, the electric field will be in the direction of current. In electric field's direction, potential decreases. Just remember one line: along current, potential decreases. Okay, along current, potential decreases, right? Okay, let's learn about cells or batteries. A battery is the source of energy that gives charge energy to move in electrical circuits. Okay, so the symbol of battery is something like this. The bigger line shows higher potential and the smaller line shows lower potential. Okay, if it is an ideal cell, the potential difference across it, the potential difference between A and B will remain constant, and VA minus VB, as we can see, A is at higher potential. So VA minus VB is equal to, in case of ideal cell, it is equal to EMF of the battery, which is E. It is generally written in the question just near to battery. Okay, notice here the potential difference depends only upon the polarity. Okay, potential difference depends upon the polarity. The bigger line is positive with respect to the smaller line, right? It does not depend upon the direction of current or magnitude of current. It does not depend upon direction of current or magnitude of current. Okay, so if the current is flowing in it is still, or if the current is flowing in it in right direction or in left direction, or whatever be the magnitude of the current in this, the potential of A will be higher and the potential of B will be lower, and the difference will be equal to EMF of the battery, right? But remember one thing: if battery supplies current like this, we say battery is giving energy, battery is supplying energy, and if battery is supplying energy, we say the battery is getting discharged. And if this is the direction of current, okay, means current is going from positive terminal to negative terminal inside the battery, then we say the battery is gaining energy, battery is absorbing energy, and then we say battery is getting charged. So direction of current decides whether the battery is getting discharged or charged. Okay, so let's move a little. Usually we see real batteries also in the circuits, and real batteries are those which have a little resistance between its terminals. The resistance can be shown outside the cell, okay, but the actual location of this resistance is inside the terminals or in between the terminals. So you can say this real cell or the real battery is a combination of an ideal battery and a resistance. Look carefully. If the current is like this, means the positive terminal of the battery is supplying current, then we say the cell is discharging, means it is giving energy, right? Okay. And as you know, this terminal is always positive with respect to this one, and current is towards left. So current is towards left, let's say I. In resistances along the current, you know, potential decreases. I just told you along current potential decreases. So this terminal is higher and this terminal is at lower potential. Can you see these two potential difference are in opposite sense? And if these two potential difference are in opposite sense, they are trying to cancel each other. So now potential of A minus potential of B. It is also called terminal potential difference across battery. Terminal potential difference across battery, and it is equal to, because this and this are in opposite sense, the potential this is E minus I times R. So try to remember during discharging, if EMF of the battery is E, but across the battery, we get a little lower potential. So in case of discharging, the terminal potential difference across the battery is lower than the EMF. Okay, always remember this. But what happens if battery is getting charged? The direction of current is like this. If direction of current is like this, let's mark polarities. The cells polarity are always like this. But if current is moving towards right, along the direction of current, potential decreases. So in the resistor, in the internal resistor, the polarity is like this. The potential difference is current times resistance. And now you see these both are in same sense. These two polarities are in same sense. Then the VA minus VB, or simply the terminal potential difference, equals E plus IR. E plus IR. So remember this fact. The terminal potential difference across battery can be higher than the EMF of the battery in case of charging. It can be lower than the EMF of the battery in case of discharging, or it can be equal to the EMF of the battery if battery is neither charging nor discharging, or you can say if battery is not giving current. Okay, so this was something about resistances and batteries. Then we will learn a very important tool of solving circuits, that's Kirchhoff's current law. The Kirchhoff's current law is very simple, and it is based upon the fundamental fact that charge is conserved. So it is based on conservative nature of charge. So suppose we see in a circuit that at a junction few currents are coming and few currents are going. As you can see, I think I1 and I4 are incoming currents and I2 and I3 are outgoing currents. So always remember, sum of incoming currents, sum of I incoming is equal to sum of I outgoing. So I can say the incoming currents are I1 and I4. So I1 plus I4 equals outgoing current sum is I2 plus I3. So I2 plus I3. So sum of incoming current equals sum of outgoing currents. That is simple. But remember one point. This law is not only valid for a point or for a junction. This junction is also called node. This junction is also called node. This is also applicable if you take a part of the circuit or a resistor or a battery. Like suppose these are 2 points, let's say A and B, and we have a battery or a resistance or any part of circuit between A and B, and we see these currents I1, I4, I2 and I3, and we are thinking about to develop or write a relation between these four currents. You can easily take this part a node. This can also be taken as a node, and you can see on this node I1 and I4 are incoming current and I2 and I3 are outgoing current. Okay, there may be some current between the node or in the node also, but that is internal to the node. The net current incoming on the node will be equal to net current outgoing from the node. Okay, so it's still here also you can write I1 plus I4, sum of incoming current equals to sum of outgoing current I2 plus I3. I'll tell you one example about this. Okay, so let's move for a few questions. In this question, it is written that in this circuit, they are asking what is the current in each resistances. What is the current in each resistances? And I'll solve this using few fundamentals. I'll again say you try it yourself and then look for solutions. But remember one point, in the circuit, in any circuit, we have a freedom to choose any one point's potential to be zero. We can choose a reference level at any point. So I can choose this point's potential to be zero. this is a symbol of earthing, and if I earth some point, the potential of that point becomes 0, right? Remember, we have this freedom that I can take any one point's potential to be 0 in any circuit. Okay. So if this is at 0 potential, I have assumed it like this. Okay. So if I move from here to here, can you see I have crossed a battery? And I have crossed a battery from negative terminal to positive terminal. So potential of this point will be higher than this. And how much higher? Equal to EMF of the battery, 2 volt. So potential of this point will be 2 volt. Always remember. Okay. If potential of this point is 2 volt and I move further along this direction, I cross one more battery. If I cross one more battery, actually it is ideal battery. They haven't said the battery has some internal resistance, so I'm assuming them to be ideal batteries. So if I cross this one more battery and come to more higher point, so if you cross this battery, you know this point's potential must be 2 volt higher than this. So this point's potential is 4 volt, right? If this point's potential is 4 volt, this point's potential will be 6 volt because it is more higher than 4 volt. If this point's potential is 6 volt, this point's potential is also 6 volt because we haven't crossed anything. We didn't cross resistance, we did not cross any battery. So we have potential 6 volt here. If it is 6 volt here, if you move in this direction, can you see now we are moving towards negative terminal of the battery. And if I move towards negative terminal of battery, the potential will drop by EMF of the battery. So if EMF is 2 volt, here potential is 6 volt, it will drop by 2 volt and potential of this point will be 4 volt. Similarly, potential of this point would be 2 volt. And if this is 2 volt, a 2 volt drop further and potential of this point is 0 volt. Now, can you see? This is the resistance and across this resistance, we do not have any potential difference because here potential is 4 volt, here also potential is 4 volt. So according to Ohm's law, remember Ohm's law is applicable for resistance. So according to Ohm's law, if potential difference is 0, whatever be the value of potential doesn't matter. If potential difference is 0, the current would be 0. So we have 0 ampere current flowing in this 1 ohm. Similarly, potential difference across these resistance is also 0. 2 volt here, 2 volt here. So here also current will be 0. And here also current would be 0 because the potential difference is 0. So in all three resistance, we have 0 ampere current. So correct answer is A. Okay. Let's move to next question. Now, in this question, they are asking us, what is the value of current? What is the value of current? Okay. When we close the switch S. So when we close the switch S, this point's potential becomes 0. Can you see that? This point's potential is 0. This point's potential they have given as 20 volt. B's potential is, the potential of B is 10 volt. Actually, in battery, you know the potential difference. I told you about that. But in resistance, you know potential difference when you have value of current. And since the value of current is not known, we cannot know the potential difference across this 2 ohm without solving it. So when you cross this 2 ohm, you do not know what is the potential at C point, right? So let us assume the potential at C point is X. Okay, let us assume potential at C point is X. And can you see the current I1 is coming towards C, I2 is coming towards C, and I is going from C. So according to KCL, the sum of incoming current equals sum of outgoing current. What I can write is I1 plus I2 equals I. Okay. Now, what is I1? You know, according to Ohm's law, the I1 is equal to potential difference upon resistance. So if I1 is like this, remember I1 is like this, I told you along current potential decreases. So if along current potential decreases, 20 should be bigger than X. Okay, so magnitude I1 should be 20 minus X, the potential difference, divided by resistance, which is 2 ohm, plus the value of I2. Now guess the value of I2. As I2 is towards left, the potential X should be lower than 10 and magnitude I2 should be 10 minus X divided by 4. So 10 minus X divided by 4 equals to I. If I is towards downward, so obviously the electric field is downward in this resistance, so this must be at higher potential than this. So X is bigger than 0 according to our assumptions. Okay, so I'll write X minus 0 by 2 as I, X minus 0 by 2 or just X by 2. Now solve this. Okay, so 20 by 2 is 10, 10 by 4 is 2.5, and bring X by 2 and X by 4 on the right hand side. X by 2 plus X by 2 is X, plus X by 4 is 5 by 4X. We have 5 by 4, or you can say 1.25X. And here we have 12.5X. So solve it and you will get X equals 10 volt. Okay. So if X equals to 10 volt, right? If X equals to 10 volt, here the potential is 10 volt. I can write the potential is 10 volt. And if at this point potential is 10 volt, okay, the potential difference across this resistance will be 10 minus 0, that is 10 volt. And the value of current I can be written as 10 minus 0, it is the potential difference across the resistance, divided by 2, that is 5 ampere. So correct answer is 5 ampere. Now we can calculate the current in every branch of the circuit. Like if here potential is 10 volt, here also potential is 10 volt. If both potentials are same, there is no potential difference across this resistor. And if there is no potential difference across this resistor, what should be current in this? 0. So I2 is actually 0 here. If this is 20 and this is 10, so the difference is 10 and 10 by 2, the 5 ampere. The 5 ampere is going towards this and that is going in this path along this, because current here is 0. That is the actual result. Okay. Now next move to next question. Again, it's a very simple question. I think you all can solve it. So please solve it and then see solution and answer. Okay. Here again, we are given two batteries of 10 volt each. And as I told you, we have a freedom to assume one point's potential to be 0. So let us assume the potential of this point to be 0. If potential of this point is 0, potential of this point is also 0. This point is also 0. This point is also 0, because if you do not cross any element, potential will not change. Potential will change when you cross a battery. Potential will change when you cross a resistor. But if you are moving along conducting wires, zero resistance wires, potential will not change, right? Now if you move from here to here, you can see there is a rise of 10 volt because we have a battery. Okay, we have a battery. This terminal is negative, this terminal is positive. Can you see that? So we have a rise of 10 volt, so potential here is 10 volt. And if you move further, can you see there is a drop of 10? There is a drop of 10 volt. So if potential at this point is 10 volt, then we have a drop of 10 volt, so potential at this point too becomes 0 volt. Okay. And now you know potential of each point. So obviously the current here, can you see potential is decreasing in this direction, in upward direction. If potential is decreasing in upward direction, current will be in upward direction, because in the direction of current, potential decreases. Remember. So current would be obviously potential difference divided by resistance. So current I equals to, current I in R1 equals to 10 divided by 20, that is 0.5 ampere. And this current in R2 is 0. Guess why? Because potential difference is 0. So currents are 0.5 ampere and 0, and the correct option is A. Okay. Now let's move for next question. Again, it is a very simple question. It needs a little observation, but I assure you it's a very simple question, and you all can solve it. So let's solve it. Okay. they say the current I1 is minus 0.3 ampere. Minus 0.3 ampere means either you take the value I1 as minus 0.3 or you just flip the direction of I1. So let's flip the direction of current I1. They have shown downward current. Let us assume I1 is upward and the value I1 is 0.3. Now negative is not required. Okay. I1. I4 is 0.8. So we have I4 here and it is 0.8. Okay. I5 is 0.4. So we have I5 here and it is 0.4 ampere. Okay. See, this is the I5 and the I5 is going in this direction. So this I6 is actually I5. Okay, because in this path current will be same. There is no other way to go for current to go. Suppose at this junction the incoming current is 0.4. Obviously the outgoing current should be 0.4 according to KCL. So I6 is simply 0.4. Now let us guess the other values. Okay, at this junction can you see the incoming current is 0.8, the outgoing current is 0.4. So if incoming current is 0.8, this is 0.4, where is the difference going? 0.8 incoming, 0.4 outgoing. Obviously the remaining 0.4 is going in this direction, 0.4 ampere is going in this direction. So obviously I3 is 0.4, right? I3 is 0.4. Now come to this junction. Can you see the incoming current at this junction is 0.5, not 0.5, 0.4, 0.4 and 0.3. 0.4, 0.4 and 0.3 are incoming currents. So outgoing current must be sum of all three, that should be 1.1. So I2 is 1.1. So we have to answer I2, I3 and I6. So I2 is 1.1, I3 is 0.4 and I6 is 0.4. So answer must be 1.1, 0.4, 0.4. So correct answer is B. Okay. Let's move to next question. But remember, you have to see this series in parts of maybe 1 hour or 1.5 hours each, so that you will learn and remember everything, right? Okay. Again, we have a very simple question and they say the value of current in 6 ohm resistance. We have 6 ohm here, okay, and we are asked what is the value in this resistance. See, again it is a very simple question. You all solve it and then look for solution. Again we have a freedom to choose any one's point to be 0, any one point's potential to be 0. So let us assume potential is 0 here. It is 0 here. It is 0 here because we are not crossing anything. Potential at this point automatically becomes 140 volt. See, potential here is 0. So this point potential becomes 90 volt. I think you all can see because we are going from negative to positive terminal. You all remember the smaller line is negative and the bigger line is positive. So if we go from negative to positive terminal, potential increases. So here we have 140, here we have 90, but here we cannot reach without crossing resistance. So if we cannot reach this point, let us assume this point's potential to be x. If this point's potential to be x, okay, now let us assume some arbitrary direction of current, okay. So the next step is assume current. Actually we do not know what is the value of x. So actually it is not required also. You can assume any value of x or any direction of current, okay. So just not looking at the values, I am assuming current I1 in this direction, I2 in this direction and I3 in this direction, right? You can choose any different values also, like I1 and I3 are outgoing and I2 incoming. You can choose any value. Believe me, you can choose any value or any direction, but I have chosen all currents going outward. If all currents are going outward, sum of outward currents or outgoing currents is I1 plus I2 plus I3, and sum of incoming current 0, because there is no incoming current I have assumed, so incoming current is 0. Okay, this may not be the true result, but you can assume it this way. There is no problem at all. Okay, now let's write the values. I1, see, I1 is towards left, so I'll write I1 as potential difference upon resistance. Potential difference is x minus 140 divided by 20. X minus 140 divided by 20. Some of you may say, okay, the value of x by guess should be lower than 140. So if it is lower than 140, the equation will tell you it is lower than 140, and then I can correct the direction in answer. Okay, but here it all works. So I1 is x minus 140 by 2. Let's write I2. I2 is x minus 0 by 6. So it is x by 6 plus I3. I3 is x minus 90 by 5. Remember, x minus 90 by 5. So let's write x minus 90 by 5 equals to 0. And now let us solve for x. Okay. If we solve for x now, see, x by 20, okay, x by 20 plus x by 6 plus x by 5, right, equals, let's take negative terms on the right hand side. So 140 by 20 is 7 and 90 upon 5 is 18, 7 plus 18. Now I am taking 60 as LCM, and if you take 60 as LCM, you have 3x plus 10x plus 12x equals 25. Okay, so 3x plus 12x, 15x plus 10x, 25x. 25x by 60 equals to 25. So this gives x equals 60 volt. So now we know the value of x. X is 60, and if x is 60, so current here in this way will be 60 minus 0 by 6. 60 minus 0 by 6 means 10 ampere. So current in 6 ohm is simply 10 ampere, and the correct answer is C. Okay. Now we have answer, but if you want to find, you can find current in this resistance also. How? This is 140. This is 60. So obviously 140 is bigger than 60. So the actual direction of I1 would be towards right. Remember, the actual direction would be towards right. And the difference of potential is 140 minus 60. How much? 80. And 80 divided by 20 is 4. So the value of current in this should be 4 ampere. And similarly, 90 minus 60 is 30, and 30 by 5 is 6 ampere. And obviously 4 and 6 are incoming current, and 10 ampere outgoing current. 10 ampere outgoing current. KCL is satisfied. This is how we solve a complete circuit. Okay, let's move to next question. Again, it's a very simple question, but some of you may find it tricky. So solve it yourself first and then look for solution. Okay, then look for solution. They are asking the potential at point B with respect to potential at point A. Potential at point B with respect to potential of point A. So again, as I told you, you can choose any one point's potential to be 0. This is permitted. Okay, so I am choosing potential of A to be 0 volt. If it is 0 volt and I move in this direction, so always move in the direction where you see ideal batteries, because along ideal batteries you know all the potential differences. Okay, so if it is 0 volt and you move from negative to positive terminal of the battery, the potential difference across the battery is 1 volt. If this point's potential is 0 volt, potential of this point will be 1 volt. Also see current. 1 ampere is coming in this direction. So current here is 1 ampere. Okay, current here is 1 ampere. I think you all can see at A 1 ampere is coming. So 1 ampere should go. Okay. So 1 ampere is coming in this direction. 2 ampere is going in this direction. Okay. So obviously 1 ampere is coming, 2 ampere is going. This is not possible. It is only possible if 1 ampere current comes from upward direction like this. So now I know what is the current in this 2 ohm resistance. And we also know the direction of current in 2 ohm resistance. It is towards downward. Now you know along current potential decreases. The reverse is also true. In the opposite direction of current, potential should increase. Okay. So what is the potential difference across the resistance? Use Ohm's law, and according to Ohm's law, the potential difference across this resistance is current multiplied by resistance, 1 ampere multiplied by 2. So we have 2 volts potential difference. Okay, 2 volts potential difference, right? But along current, potential decreases. So this would be positive and this would be negative. Now, if potential at this point is 1 volt, you go towards this point D. Now you can, because you know the potential difference. So potential at D should be 2 volt higher than potential of this. So obviously the potential at D becomes 3 volt. And if potential at D becomes 3 volt and you go towards B, you have a battery there. But battery's polarity is positive left, negative right. If battery's polarity is positive left, negative right, if you go in this direction, potential will drop by 2 volt. And if potential drops by 2 volt, 3 volt minus 2 volt is 1 volt plus 1 volt. So potential of B is 1 volt. Now you compare potential of B as 1 volt. Potential of A is 0. So potential of B with respect to A is obviously 1 volt. So correct answer is C. Okay. So you can solve very easily all the questions. Okay. Over to next question. Okay. So we have this question, and here they say what is the current in the wire joining B and D. Many students make mistakes in this question. Why? Because they think, okay, BD is a conducting wire, BD is a resistance-less wire, and if BD is a resistance-less wire, the potential difference should be 0, and if potential difference is 0, the current should be 0, but this logic is wrong. Okay, why? Because BD is not a resistance. Okay, BD is not a resistance, and if BD is not a resistance, I'll give you more than one logic. The first is BD is not a resistance, and if BD is not a resistance, Ohm's law will simply not apply. Ohm's law is not applicable here, so you cannot think with this logic that if potential difference is 0, current is 0. It applies only to resistances. The first argument. The second argument is, if you assume it to be a 0 resistance wire, okay, let us assume it to be a 0 resistance wire, you can say the potential difference is 0 according to Ohm's law, as V equals to IR. Potential difference is 0, current and R is 0. Obviously, if 0 equals to 0, I can take any value, not me, this current I can take any value. Okay, I think you all remember, if I is 0 by 0, it can take any value, like it can be 1 ampere, 20 ampere, 1000 ampere or million ampere. It can take any value. So by using Ohm's law, you cannot decide the value of current in this wire. So what to do? Let us solve it in a different way. Okay. Again, I am assuming one point's potential to be 0. Let's say this point's potential is 0 volt. If this is at 0 volt, this is at 0 volt, this is at 0 volt, this is at 0 volt. But if you cross this battery and you come to positive side, the potential of this point will be 20 volt. Potential of this point will be 20 volt, 20 volt. Okay. Now we cannot reach point B from left side or from right side because there is resistance between them. So I am assuming the potential of B as X, and as BD is a resistance-less wire, the potential of D should also be X. Potential of B and D both are X. Today I also told you that you can take any part of the circuit 2 as node. So now, as I do not know the current in BD, I will not take B as node. I will not take D as node. I will take B plus D as node. And can see from this node only resistance are connected. So I'll assume again the current in this direction say I1, current in this direction say I2, in this direction say I3, and in this direction say I4. For simplicity, I have assumed all currents in outward direction. That gives you very simple KCL or Kirchhoff's current law, that I1 plus I2 plus I3 plus I4 as outgoing current and equals to sum of incoming current as 0. It can be simply written like this. Okay. Now let us write values of I1, I2, I3 and I4. I1 is simply x minus 20 by 1. Let us write x minus 20 by 1 plus I2. I2 is x minus 0 by 2. X minus 0, that is x by 2, plus I3, x minus 20 by 4. Let us write x minus, not 40, 20 by 4, or plus I4. I4 as x minus 0 by 3. So have x minus 0 as x by 3, and this sum equals to 0. Let's again solve for x. See, we have x here, x by 2, x by 4, x by 3. So if I take 12 as LCM, x by 1, it becomes 12x, x by 2 becomes 6x, x by 4 it becomes 3x, x by 3 it becomes 4x, and take all negative terms on the right hand side. So we have 20 by 1 as 20 and 20 by 4 as 5. Now let's sum up. So we have 12x plus 6x, 18x, 18x plus 3x, 21x, 21x plus 4x, 25x. So 25x by 12 equals to 25. You have x as 12 volt. We know x is 12 volt. Let's rewrite there. We know the potential of x as 12 volt. 12 volt. And now calculation of current is very easy because you know the potential at this point. See, we have 20 volt here, 12 volt here. So difference is 8 ampere, 8 volt. And if difference is 8 volt, potential is decreasing in this direction. So correct direction of I1 is towards right. And potential difference is 8 divided by 1. So we have 8 ampere towards right. Okay. Now from B to this point, we have 12 volt here, 0 here. So the potential difference is 12, and 12 divided by 2 is 6. So we have 6 ampere here. And now this can easily be guessed that at this junction 8 ampere is coming, 8 ampere must go. So if 6 ampere is going this way, the current in BD should be downward and 2 ampere, because 2 plus 6 is 8, incoming current is also 8. So correct answer is 2 ampere. Option correct is B. Okay, over to next question. Let's keep solving. Okay, before we solve further questions, let's learn one more rule given by Kirchhoff's, and this is Kirchhoff's loop law or Kirchhoff's voltage law. And we simply call it KVL, Kirchhoff's voltage law. Okay. Let us see what is Kirchhoff's voltage law and why or when it is used. When you see multiple elements in a loop, multiple elements, multiple resistances, multiple batteries, and the number of loops are less, then every point becomes node, and if you write node equations or use KCL, the equations becomes very large. So in those cases where we have less number of loops and many elements, we have many elements, we'll practice also, don't worry, we have many elements, less number of loops and many elements, we use KVL. And it is based upon the conservative nature of electric field. I think you remember the electric field, electrostatic field is conservative, and in conservative field, if you move in a loop, the integral, closed integral E dot dl is 0. Closed integral E dot dl is 0. So if you move in this loop and write E dot dl is what? What is E dot dl? E dot dl represents an elemental potential difference. So if you write potential difference of each element, obviously in some order, and you reach from one point to that very point after traveling in a loop, okay, you will get the total potential difference to be 0, and that is the Kirchhoff's law. Sum of all potential differences in all elements is 0. Okay, as electrostatic field is conservative, we also say this is based upon conservation of energy. Now we will learn how to write KVL, and then we will learn how to use KVL in problems. Okay, so let us learn. Whenever you see and wish to apply KVL, always remember we have to follow these 3 steps. The first is assume directions of current and values of current. You can assume directions of current and values of current arbitrarily. There is no need to guess the right direction of current, just assume currents. Okay, but if you assume currents keeping KCL in mind, you will notice that the number of unknowns will be very less. Okay, so assume currents, so you have to assume currents in the circuit with directions obviously. Mark polarities. So you have to mark polarities according to your directions of current assumed. So whatever directions you assume in a circuit of current, mark polarities according to that. This may seem you a little difficult, but when I'll tell you the exact procedure, it is not that difficult. First, let us learn what we have to do. Assume currents arbitrarily, mark polarities, and then we will write KVL. Writing KVL means write all elements potential differences and make it equal to 0, but travel in a full loop, right? So we have a loop. Can you see a loop? It has many elements. Okay, this loop may be a complete circuit, or it may be a part of a bigger circuit. Okay, so I am assuming this to be a part of some bigger circuit, and I am trying to apply KVL in this loop only. So I am assuming the points are, say, A, B, C and D. Okay, I'll start from A, we'll go to B, C, D, and I'll return to A, and then the loop will be completed. Okay, so I've selected loop A, B, C, D. Now the first step is assume currents. So I can assume currents in any direction I want. Okay, so let us say here the current is I3. I've just took I3 because this is V3, so I've assumed I3. Okay, no worries. Current here is I2. Here current is say I1, and here it is say I3. Okay. Do not worry about the values of currents. I'm just telling you how to write equations. Then assuming current will be a simple part, I assure you. It will be a very simple part, and that we will do in real questions. Okay. So suppose I've just assumed currents like this. After assuming currents, let's move from A to B. If you want, you can mark polarities also, but that second step is not that important because you already know. In battery, the bigger line is positive with respect to the smaller line, and in resistances, potential decreases in the direction of current. So if you remember this, marking polarities is not important. Okay, so I'm starting how to write. Let us learn how to write KVL. Start from A, okay, and from A, if you go to B, can you see the potential is dropped because you are moving from positive side to negative side, and the drop of potential is V3. So let us represent drop as negative and rise as positive. So if I go from A to B, potential is dropped by V3, so I'll write minus V3. Then I'm at B now. I'm moving upward. I'm going towards C. So if I cross R2, can you remember? Do you remember? Along current, in resistances, along current, potential decreases. And if potential decreases, the potential will decrease. And the decrease of potential would be according to Ohm's law, I to R2. Because you know the difference of potential is IR. So decrease of potential will be I to R2. As it is a decrease, I'll write minus I to R2. Now I'm at this point and I'll go from here to here. Can you see I'm moving from negative terminal to positive terminal of battery? And the positive terminal of battery is at higher potential than negative terminal, and the potential difference is equal to V2. So from here to here, the potential will increase. Okay. So I'll write plus V2. Now where I am at point C. Okay, I am at point C. From C, I am going towards D because the flow direction will be same in one equation. Okay, so if I move from here to here, can you see again the potential is rising in this battery. From here to here, potential is rising, and the rise of potential is plus V3. Now I am crossing R1. Okay, in R1, in resistances, what you know is in the direction of current, potential decreases. So reverse is also true. In opposite direction of current, the potential will increase, and it will increase by, think, what is the value? According to Ohm's law, the potential difference is I1 R1. So it will increase by I1 R1. Now I am at point D, and from D I'll move towards A. See, I'm moving in the direction of current, so potential will drop, and it will drop by minus I3R. Let's write minus I3R3 here, minus I3R3, and we reached point A. If we reached point A after starting from point A, so we have covered all the elements potential difference, so their sum is obviously 0. So this is the way to write KVL. Always remember, when you go from positive terminal to negative terminal, potential will drop. In battery, in fact, from negative to positive, the potential will rise. In the direction, in resistances, in the direction of current, the potential drops. Opposite to direction of current, potential rises. If you have any doubt in this, okay, rewind this video for 2-3 minutes, see it again, and definitely you will learn. Still you have some trouble, then look for few examples I am going to solve. Okay. So here we have another example, and in this they say, what is the potential difference VA minus VB? What is potential difference VA minus VB? Okay. In this question, I will apply KVL from point A to B. Okay, but you will say, How is it possible? The KVL is only valid in closed loops, but it is not true. KVL is also valid in open loops, okay, or in a single branch. But what you have to do, you have to follow the simplest steps I am telling you, okay. So, how you have to write KVL? Learn from this question in open loops, okay. But before that, let us just guess the values of potential differences, because the current is known. See, if current is 2 ampere here going towards right, the direction of current is towards right. In resistances, along current, potential decreases. So in this resistance, potential will decrease from this side to this side. And drop or difference of potential according to Ohm's law will be I times R. I is 2 ampere, R is 2 ohm. So the I times R is 4 volt. So we have a drop of potential difference from here to here equal to 4 volt. Okay. Across battery, the potential is simply 3 volt. Now the 2 ampere is also flowing in this resistance. Can you see? The 2 ampere is also flowing in this resistance, and along current potential decreases. So we have this as positive, this as negative. And what is the potential difference? The current times resistance. So current is 2 ampere, resistance is 1 ohm. So this is 2 volt. Okay. So as I already know the value of current, I have written the potential difference directly. Okay. Now from A to B, how you have to write KVL, let us learn from here. If you are not going to return on A, start with VA, potential at A. Always remember, if you are not going to return on A, start with VA. Now VA. Now from this point to this point, as you can see, the potential is dropped by 4 volt. So if potential is dropped, means minus 4. Okay. Now from here to here, I'm traveling from A to B. So after traveling resistance, I have a battery in a way. And if you cross battery from left to right, you can again see the potential is dropped by 3 volt. So I'll say minus 3 volt. Let's not write unit right now. Then we have resistance, and in resistance also potential is being dropped by 2 volt. So I'll say minus 2. Okay, and now I have reached point B. If I have reached point B, just write equal to VB. So remember, here also I could have started with VA, and from VA I could have written this whole equation, and since I am ending at point A again, I can write V again, and VA will cancel, and this is obviously the correct answer, correct equation. But so VA and VA will cancel here, right? But in this equation, in this question, actually we are starting from A and ending at different point. So we have to write KVL like this. If you are starting from A, start with VA. Then the method is simple: minus 4, minus 3, minus 2, and then write an equal sign and then write VB. Now if you bring VB on the left side, you will have VA minus VB, and bring 4, 3 and 2 on the right hand side, you will have plus 9 volt. So correct answer of VA minus VB is simply 9 volt. Okay. Okay, then next question. Here they have made a big network, and they are asking you this value of current in this branch. Okay, can you see this 4 ohm is connected to this 4 ohm, and there is a jump here. Okay, there is a jump here. The jump says this branch is not connected to this vertical branch of 5 ohm, 5 ohm. Okay, this branch is not connected to this branch. So you can think this branch as a separate branch. And we are asked what is the current I1 in this branch. Okay, so obviously I can take this as my loop. I can start from this point and now I can apply KVL. If I apply KVL along this direction, I start from this point, from here to here, the potential increases by 8 volt. I'll start with 8. Then from here to here, along current, you know potential decreases. I've assumed the current towards right, so along current potential decreases. In resistance, potential differences I times R, so we have potential differences I1 into 4 minus I1 times 4, because along current potential decreases, that is why a negative sign here. Okay, then again the same current is going in this 4 ohm also, again towards right, so minus I1 times 4 equals to, now can you see there is nothing in between and I reach this point. So loop is completed. I can write equal to 0. There is no need for solving entire circuit. I now know the value I1, and I1 is 8 by 8 as 1 ampere. So correct answer is D. Okay, next question. Now some of you may solve it obviously, but I'll tell you some very important trick to solve this. Okay, obviously from 1 ampere, actually we are asked this current I1. Okay, so suppose from here currents are going, and from here the current will split into two resistances, here and here. Can you see this is 1 ohm, this is also 1. This path is of 1 ohm resistance, this path is of 1 ohm resistance. Both paths are identical, and if both paths are identical, current will be split into two equal parts. And by this logic I can say if this is I1, this will too will be I1. And if this is I1, this is I1, this is I1, this is I1, so this will be 2I1. And here they will merge again, and in this 2 ohm the current will be 2I1. Okay, and now can you see one path is complete? For writing KVL, I need at least one path, and that is complete. And if it is complete, let's write KVL starting from this point. I'll go here and come back to this point. Okay, so let's write. From this point to this point, potential increases by 1 volt. Okay, then we have nothing till this point, and if I cross this 1 ohm resistance, obviously in the direction of current potential drops. So the potential will drop by I times R. I is I1, R is 1 ohm. Then I come to this resistance 2 ohm, and in 2 ohm the current is 2I1 and current is towards right, so potential will again drop, and it will drop by minus 2I1 multiplied by 2 ohm equals to 0, because I have reached this point again, so 0. Now you can solve. I think 5I1 is equal to 1, so I1 is 1 by 5, that is 0.2 ampere, and the correct answer is A. A very simple question. You don't have to assume more than one unknown. Again, it's a very simple question. Let us solve it. Okay, they are saying we have two cells of EMFs 2E and E, and their internal resistances are R1 and R2. They haven't shown, but they are saying the batteries have internal resistances. So if batteries have internal resistances, let's show R1, and here we have R2. Okay, now we get one circuit. It is a one loop I told you, if you have less number of loops and many elements in it, there are 3 resistances and 2 batteries in it, there are many elements in it, the KVL will be best. Okay, so let us apply KVL. Okay, let us assume the current is I. In all three resistances, current will be I. Okay, so I can write, start from any point, from here, let's say U cross E, you can write E. You also cross 2E, let's write 2E. And we have to cross 3 resistances R1, R2, R3. Obviously in the direction of current, so potential will drop. So it can be written as I times R1 plus R2 plus R. Okay, so I becomes 3E divided by R1 plus R2 plus R. Okay, you can remember this result if you anytime see a single loop problem. So in single loop, the net current would be total EMF divided by total resistance. What is total EMF? If all batteries have same kind of polarity, the total EMF will be sum of all EMFs of the battery. And if any battery has opposite polarity, give it a negative sign. Okay. So I is 3E divided by R1 plus R2 plus R. Okay. But they have said something else. They are saying find the value of R such that potential difference across first cell is 0. This is the first cell. The current is like this. And across this cell, potential difference is 0. Potential difference is 0. I think you remember maybe 1 hour ago, I told you that potential difference across complete battery is called terminal potential difference. Can you see this battery is discharging? And if this battery is discharging, the terminal potential difference across this battery, let's write it as V, equals EMF 2E minus I times internal resistance is R1. Okay, and this terminal resistance is, they say it is equal to 0. They are saying the terminal potential difference across the battery is 0. Okay, so this is 0. And if this is 0, from here you can say I equals to 2E by R1. So I'll bring this value I, put it here, and I also equals 2E by R1. From this equation, E got cancelled, and now I have, just listen, 3R1 equals 2R1 plus 2R2 plus 2 capital R. And now you know the value of capital R. So capital R will be actually R1 by 2 minus R2 after solving this simple equation. Just cross multiply and solve, and you will see the answer is B. Okay, so over to next question. Okay, we have again few fundamentals, right? Actually, now we will learn the power in DC circuits. Obviously, power is the most important thing in physics, and we have studied this much of physics for power actually. So, when a battery is supplying current, what happens? Obviously, the charge, the positive charge is going from left hand to right hand. If I consider a little time dt, the charge in little time dt will be actually I dt. And I dt charge will pass through the battery, means from negative potential to positive potential. Sorry. From negative to potential to positive potential. So, the work done by the battery would be the potential difference times charge. So, this is the work done by battery. Okay. and you know the rate of work done, dW by dt, is actually power. So bring this dt here and you will see the power equals to V times I. So in this first circuit, when the battery is discharging, means it is supplying power to the circuit, I'll say the power delivered by battery or by the cell is V times I. But in this case, as the battery is absorbing power, battery is gaining power from some external circuit, the power absorbed should be written as V times I. Or you can also say, in this case, power delivered by cell is minus Vi. So remember this formula, a battery of EMF V or E, sometimes I write V or E, doesn't matter. So if EMF is V, the power delivered by battery will be Vi. If it is E, then it will be EI, simply. And if the current direction is like this, the battery is gaining, but battery is absorbing power equal to V times I. Okay. What happens to the power that is being supplied by battery? When current passes through a resistance, that power is dissipated. That power is actually dissipated. Okay, as heat inside resistor. So power dissipated in resistance. Again, see, if current is being passed in a little time dt, the charge flown through the resistance will be I dt. Okay, if it is crossing a potential difference of V, the work done here is V times charge, that is Vi dt. So the work destroyed here, or you can say the energy destroyed here, is dW equals to Vi dt. So the rate of energy being destroyed, that is power being destroyed or dissipated, equals dW by dt, and it becomes Vi. How I can say power is being destroyed? How I can say the power is being delivered? The simple answer is here. The potential of charge is increasing. If potential is increasing, potential energy is increasing. So if charge comes from this point to this point, energy is increased. That is, power is being delivered. Right? In this diagram, here the charge was at higher potential. Now at this point the charge has lower potential, means the energy is dissipated because the energy of charge is decreasing. So here I say the power is being dissipated. So power being dissipated equals V into I again. Okay, V into I. But since in resistors Ohm's law is applicable, okay, and Ohm's law says V equals to IR. So if I replace this V as IR, power also becomes I square R. Or if I replace I as V by R, power also becomes V square by R. Okay, so for resistors, we do have three formula for power: Vi, I square R, and V square by R. Remember, for resistors we have three types of formula. So you can use any one whenever required. Okay. Now what happens to this power dissipated? Actually, this power is converted into heat. Okay, and that is why resistances or bulbs heat up when current is passed through them. Okay, so if we want to find the heat developed in time t, we should simply integrate power with respect to time. So in time t, power with respect to time will give you Vi dt will give you Vit, I square R dt will give you I square RT, and V square by R dt will give you V square by RT. Okay, so this is the heat developed. Okay, so suppose in some question they say you the mass of the resistance is M, the specific heat of the resistance is S. What is the rise in temperature? You can simply write this heat developed as, I'm writing only one formula, you can write all three or any one of the three. Okay, so I square RT, it is the heat developed, and this will go in increasing the heat energy or the internal energy of that system, and that can be written as ms delta theta, where m is the mass of the resistance, okay, S is the specific heat of the material of the resistance, and delta theta is rise in temperature. So by using this formula, this is also called Joule's law of heating, and from here you can calculate the rise in temperature of resistance. Okay, so this is the basic fundamental of geysers. In geysers, what we have resistance elements, and we plug the supply. When we plug the supply, current is passed through those resistances, and when current is passed through those resistances, in some time the heat is developed, and that is why that heat is actually transferred to the water kept in geyser, and because of that heat, water heats up, okay, and the temperature of water rises again. Okay, this is again a very important phenomenon, and this says maximum power transferred to a variable resistance. This is also known as maximum power transfer theorem. So suppose you have a battery of EMF V, internal resistance is small r, and this thing is connected to some variable resistance R. Okay, how we represent a variable resistance? If I draw one arrow on resistance like this, it becomes a variable resistance. This is the symbol for a variable resistance. Okay, so if you want to know the power transferred in this resistance, okay, power transferred in this resistance, suppose I know the current here, the power transferred in this resistance will be I square times R. But there is a very simple way also. Actually, power transfer to resistance, power to variable resistance R can also be written as, you all know that V times I, if I is the current in this circuit, V times I is the current, is the energy, actually it is the power being developed by, being delivered by the battery. Okay, so V times I is actually the power delivered by the battery, but some part of this power is being dissipated in the internal resistance of the battery itself. So what is the power dissipated in the internal resistance? I know current I know internal resistance R, so I square is small r, this much power will be wasted inside the battery. So this is the power developed by battery, it is the power wasted, the difference is available for the load resistance or the variable resistance. Now can you see this power versus I function? The V and R, V and small r are constant, the only variable is capital R and I. So here you can see power is dependent upon I. This is a parabolic result, you all know that this is a parabolic result, and this kind of parabola is similar to the projectile motion of parabola. So the graph of this I have drawn here, and from here you see at some current the power will be maximum. At some current the power will be maximum. So how to find that current? We will use simple mathematics of maxima and minima, and I differentiate power with respect to current I, because that is the only variable here. Here we will have V minus 2IR, and for power to be maximum, this derivative has to be 0. So from here you can say I equals V divided by 2R. Okay, V divided by 2R. Also, you can write I using KVL, and I think few questions back I told you, if you see a single loop problem, the current would be equal to the EMF in that loop V and divided by total resistance, and the total resistance is R plus capital R. R plus capital R. So by equating these two, now you know 2R equals to R plus capital R. And if 2R is equal to R plus capital R, this says R should be equal to small r. So that is the result of maximum power transfer theorem, and it says when external load resistance is equal to internal resistance of battery, if external variable load resistance is equal to internal resistance of the battery, the power transferred to this resistor will be maximum. Okay. And if you want to know what is the maximum power, so maximum power P max can be written as I square R. Let's make I square. So I square is V square by 4R. V square by 4R, and capital R is also equal to small r. Sorry, 4R is square, and capital R is equal to small r, so small r. So we have V square by 4 small r, and since small r and capital R are same, there is no difference. You can also write V square by 4 capital R. So this is the maximum power delivered to the external load resistance, variable load resistance. But this is not a very useful phenomenon or concept when we talk of the electricity we are using, because it says when this resistance and this resistance are equal, power delivered will be maximum. But if these two are equal resistances, the maximum power will be delivered here and equal maximum power will be wasted here. The efficiency of such system would be only 50%. Okay, so that is why a lot of energy waste. We do not use this in power transmission that we use in our electricity department, right? But this is a very useful theorem or useful concept when it comes to communication. In communication systems, as you know, the TV communication or mobile communication, the signals are of very low power. And as signals are of very low power, if equal low power is wasted, there is no problem at all. But the signal quality must be best. So that is why we use this concept in communication system, but not in electricity department. Okay. So remember the result when the variable resistance is equal to the internal resistance of the battery. There is one more thing. If there is some more resistances in the path, and they say what should be R? What should be R? In order to get maximum power in R, you should take all other resistances except this R as internal resistance of battery. Remember, if they have few more resistances in the path and this is the only variable resistance where we have to deliver maximum power, all other resistance except this should be considered along with battery or in the internal resistance of the battery. Okay, so that is about power and energy, and let us solve few problems based on this. Okay, the first, the current of 2 ampere was passed through an unknown resistor which dissipated a power of 4.4 watt. Okay, so we have unknown resistance R, the current is 2 milliampere and the power is 4.4 watt. As you know, in terms of current and resistance, the power is I square R. Remember, I square R. So R becomes power, that is P by I square, or 4.4 watt divided by 2 ampere square, that is 2 times 10 to the power minus 3 square. This is the value of the resistance R. Now they say, what is the power when an ideal power supply of 11 volt is connected across it? When an ideal voltage or voltage supply of 11 volt is connected across R, the voltage or the potential difference across R would be 11 volt. And then power can be written as V square by R equals to power. So I can write, in the place of V square, I can write 11 square divided by R equals to new power T dash. Okay. Now if you multiply these two equations, can you see in the left we have R and here we have 11 square by R. So multiplying these two, you will have 11 square in the left. We are multiplying these two, and on the right you will have 4.4 divided by 4 times 10 to the power minus 6 and times P dash. And if you solve this simple calculation, you will see P dash equals to 11 times 10 to the power minus 5 watt. So correct answer is C. Okay. Over to next question. I'm again saying all of you, please solve these questions yourself first and then look for solutions. Okay. Then look for solutions. This will be the best kind of practice for you. Here I have a battery of 3 volt and it is connected to a resistance dissipating 0.5 watt. So we have a battery of 3 volt EMF and it is connected to a resistance, let's say R, and it dissipates 0.5 watt. They say the terminal voltage of the battery is 2.5 volt. So terminal voltage of the battery, this voltage is actually 2.5 volt. Okay, you know when battery is getting discharged, the terminal voltage can be less than EMF of the battery because of internal resistance. So obviously there is some internal resistance, and finally they are asking the value of internal resistance. So I have assumed small r as internal resistance. Okay. Okay. Now see, if this potential difference across battery is 2.5, the potential difference across R is also 2.5. And if potential difference across R is 2.5, the power in R can be written as, we have 3 formula for power in resistance, VI, I square R or V square by R. Let us use VI. So power in R would be P equals to 0.5 equals to V, that is 2.5 times I. So we get current as 1 by 5 ampere. We have current in this circuit as 1 by 5. Now they are saying what is the internal resistance. I think you remember the terminal potential difference equals EMF minus I times R. Okay, so terminal potential difference is 2.5, E is 3 minus I is 1 by 5, or write it as 0.2 and times R. Okay, and I think you can solve it very easily. 2.5, 3 minus 2.5 is 0.5 and 0.5 by 2, 0.2 is R equals to 2.5 ohms. So correct answer is 2.5. The internal resistance is 2. Oh, sorry. They are not saying the value of resistance. Okay. No worries. I can solve it in a. Okay. Let's remove these calculations. In fact, they are asking a very simple question. Okay. They are saying, what is the power being dissipated within the internal resistance? Okay. Actually, you know, the power delivered by the battery is EMF times current. So power delivered by battery is EMF times current. It is equal to power by battery is 3 multiplied by 0.2, that is 0.6 watt. So answer is simple. If battery is delivering 0.6 watts, in the resistance we have power as 0.5 watt, the difference is being dissipated in internal resistance and the difference is 0.1 watt. So that is the simple question. Okay, let's move to next question. This is again a very simple question. Solve it yourself. And in this question they say the resistance develops 500 joules of thermal energy in 20 seconds. They are saying energy when a current of 1.5 ampere is passed through it. So when they are saying current, let's use a formula for current of power. So I think you remember power is I square R, and thermal energy being developed or dissipated, H equals I square R T. The H is 500 joule equals to I is 1.5 ampere square times R and times T. T is 20 seconds. Now if current is increased from 1.5 to 3 ampere, what will be the energy developed in same time 20 seconds? Okay, so let's say the new energy is H dash equals 3 square, the same resistance and equal time 20 seconds. Now divide these two, you will have H dash divided by 500 on the left and 3 square by 1.5 square, that is 4 on the right. So H dash is simply 4 times 500, that is 2000 joules. Okay, next question. This question is again asked in 21 and it is based on maximum power transfer theorem. It says for a particular resistance X, as shown in the figure, the thermal power generated in Y is maximum. Can you see Y is a variable resistance? And they are saying in Y maximum power is being generated. So I have to apply maximum power transfer theorem. And that says this, in this variable resistance, maximum power will be developed when resistance of this will be equal to internal resistance of the battery. But remember, I told you, except this resistance, all other resistances you have to include in battery. So this X and 6, they are in parallel, their combination is going to be 6X divided by 6 plus X. Okay, this is connected to this internal resistance of battery 2 ohm. This actually will be included in 2 ohm internal resistance of the battery. So net resistance in addition to this Y in the circuit is 2 plus 6X divided by 6 plus X. Okay, and this must be equal to Y, which is 4 ohm, for maximum power being delivered to Y. Okay, so if this is the result, I've made Y equal to net resistance of the remaining circuit. You will have 12 plus 2X plus 6X equals to 24 plus 4X. Okay, 2X, 6X, 8X minus 4X. So we have 4X equals 24 minus 12, that is 12. So X equals 3. So the answer is 3 ohm. The value of X is 3 ohm. Okay. Now we will learn another very important concept in this chapter, which is combination of resistance. And the first combination is series combination of resistance. So what we do in series combination, we just add resistances, few resistances, 3 or 4 resistances in series, that is every resistance comes after one resistance. Okay, so when they are connected side by side, this combination is called series resistance combination. So if I send current I from here, it has no way to go anywhere else, but it will go into R2, right? And after R2, it will go into R3. So the main feature of series combination is current in every resistance is same. Current in every resistance is same, and when you apply potential difference V to the combination, this potential difference is divided into 3 parts. So suppose across R1 the potential difference is V1, across R2 we have V2 as potential difference, and across R3 we have V3 as potential difference. So we can say this potential is divided into 3, and according to KVL you can write the total V as V1 plus V2 plus V3. Okay, so we see division of voltage and current in each resistance is same. Okay, there is one more important fact that if you try to find out the equivalent resistance of this combination, equivalent resistance means a single resistance which is electrically equivalent to this combination, then the equivalent resistance will be R1 plus R2 plus R3, means a scalar sum of all the resistances. Okay, obviously as current is passing through each resistance, there will be some power loss, and you know, since power loss is I square R and I square is same in all 3 or all n resistance connected in series, then as current is same, we can say power is proportional to R. Means the bigger resistance will dissipate more power, the smaller resistance will dissipate less power. In proportion to the resistance, power will be dissipated. Okay, so the next is parallel combination of resistance. Okay, in parallel combination of resistance, suppose we have connected R1, R2 and R3 like this, such that the 3 terminals of R1, R2, R3 are connected to one point and other 3 terminals are connected to one point. This combination is called parallel combination of resistance. The main feature of parallel combination is when you send some current I here, it is divided into 3 parts. So what we see here is division of current. So current is divided in all 3 or all 4 or all n resistances connected in parallel, right? And so suppose if we have potential V1 here, I'm assuming the potential of this point is V1, so potential of this point would too be V1, this point would too be V1, and this point's potential would be V1. And if I take potential at this point to be V2, the left end's potential would be V2, V2, V2. So can you see the potential difference across first resistance is V2 minus V1, the second resistance across the potential difference across second resistance is again V2 minus V1, and across third resistance too we can see the potential difference is V2 minus V1. So here in parallel resistance, the potential difference is same in all resistances connected in parallel, right? And the division of current, we see division of current. Okay, so division of current, same potential difference. Okay, as potential difference is same, we will be using the powers formula as V square by R because potential is same. Okay, so if you see power is equal to V square by R and V square is same, that means the potential difference is same in all, the power is proportional to 1 by R, or you can say the power dissipated will be most in the smallest resistance because of this inverse proportionality, right? And the biggest resistance will dissipate the least power. Okay, so these are the few features, and if we are asked to find equivalent resistance or net resistance of this parallel combination, the formula is 1 upon R net equals 1 by R1 plus 1 by R2 plus 1 by R3. This is very common, you must have seen this in your 10th class also. So we have 1 by R net as the sum of reciprocals of all resistances. Okay, and yes, one more very important thing which is very common in many questions, that if you take if you take n identical resistance R. So if you take n identical resistance R, we will have 1 plus R plus 1 plus R plus 1 plus R plus 1 plus R up to n times. So by adding them, we will be getting n upon R. We will be getting n by R. So R net becomes R divided by n. So always remember, if n identical resistances are connected in parallel, the net resistance will be the resistance of one resistor divided by n. So this is somehow about combination of resistances. Okay, so before we proceed, let us discuss the ratings of instruments like bulbs, etc. You must have heard about ratings. I think you must have heard about 100 watt bulb, 40 watt bulb, and nowadays the LED bulbs comes in the rating of 7 watt, 9 watt, 2 watt, etc. So whenever on some instrument this type of values are written, these are called ratings. Always they specify two ratings, okay, like 220 volt, 100 watt. Actually ratings are always two, okay, like 220 volts, 100 watt, but usually as 220 volts is very common in our homes, the voltage is 220 volts, okay, in everyone's home in India the voltage is 220 volts, so we sometimes forget to mention 220 volt, but every time we buy a bulb from a market it will be 220 volt, 100 watt, okay. So what is the meaning of this rating? It never means the bulb will glow at 100 watt. It never means, listen carefully, it never means bulb will always glow at 100 watts. It means that if you apply 220 volt across the bulb, then it will glow at 100 watt. Or the reverse is also true. If bulb is glowing at 100 watt, the potential difference across it must be 220 volt. Okay, so that is the meaning of rating. Okay, if this is the applied voltage, the power dissipated in the bulb will be this. Suppose I say in some train, I see I pick a bulb and I saw the rating is 110 volt, 40 watt. The meaning of this rating is across that bulb, if you apply 110 volts, it will glow with 40 watt power. Okay, if you apply 110 volt, it will glow with 40 watt. Okay, if you change the voltage, the power consumption may change. But what if you apply this rated voltage and the bulb is glowing at rated power? I can assume, suppose the V rated is the rated voltage. Okay, if V rated is the rated voltage and P rated is the rated power, then obviously P rated will be equal to V rated square divided by resistance of that bulb. So from the ratings actually you can find resistance of the bulb, and resistance of bulb would be V rated square divided by P rated. Okay, so like in this case, if the rated voltage is 110 volts and rated power is 40 watt, the resistance of bulb would be 110 square divided by 40. Okay, now in some case, if you give a lesser voltage to that bulb, like if you give lesser voltage like 100 volt to that bulb, obviously it will glow with low power, but the resistance will remain same. So through ratings you can find resistances. Okay, through ratings you can find resistances. So let us solve few problems based upon the facts we just learned. The first question says, look, it's a very again simple question. I'll say you solve it yourself first and then look for solution. So the question says a set of n equal resistances of value R. So we have n equal resistances of value R and they are connected in series to a battery of EMF E. Okay, let's draw this. We have a battery of EMF E and across it we have connected n resistances of resistance R each. Suppose these are n resistances and internal resistance of the battery is also R. So internal resistance of the battery is also R. In this one loop problem, the current they said is I. So let's write the current I equals, since it is a one loop problem, the current would be EMF divided by total resistance. As there are n resistances here and one resistance as internal resistance of the battery, we have n plus 1 resistances. So we have n plus 1 times R as total resistance, and this is the first equation. In next condition question says, if all these n resistances are connected in parallel and this parallel combination is put across this battery. So if all these resistances are connected in parallel, their net resistance would be R by N. As I just told you, that net resistance would be R by N, and we have this resistance along with battery. Then the new current becomes 10I. So I am writing the second equation as 10I equals the EMF E divided by, now the resistance would be R by N plus internal resistance of battery R. Okay. Let's rewrite it as, take LCM as N, bring it up. It will be E N divided by N plus 1 R. Can you see E divided by N plus 1 R is I? So I can replace this factor as I, and I'll have 10I equals I times N. If you cancel this I, N would be equal to 10. So correct answer is A. Okay, so let's move to next question. Here we have the effective resistance of a parallel combination that consists of 4 wires. So we have a parallel combination of 4 wires, and all wires have equal length, equal cross-section area and equal material. You know the resistance of a wire is given by rho L upon A. So if all 4 wires have equal length, equal area, and since they have equal same material, the resistivity will too be same. So all 4 wires have same resistance, right? All 4 wires have same resistance, remember. So if all 4 wires are connected in parallel, see, they are connected in parallel, and let's say the resistance of any one resistor is R, 4 wires parallel combination resistance would be simply R by N, and this is given as the effective resistance of a parallel connection that consists of 4 wire of equal length is 0.25. So this is equal to 0.25. It says as N equals to 4, that we had 4 wires, right? So if N is 4, R will be equal to 1 ohm. Okay. And now if you connect them in series, so all 4 resistances in series, they will become 1 plus 1 plus 1 plus 1. The answer should be 4 ohm. Okay. So the answer is D. Over to next question. This question is based upon a very famous rule, that is current divider rule. And because I had to take this question, I didn't took it in theory. Okay. So let us learn carefully. If we have a parallel combination of 2 resistances R1 and R2, can you see? We have R2 and R3 here and R1 here. So we have a parallel combination of 2 resistance R2 and R3, and a current I1 is coming through this way, and it is splitting into 2 resistors as I2 and I3. So always remember, if the main current is I1 and these 2 currents are I2 and I3, obviously by KCL you can say the first equation as I1 equals I2 plus I3, right? And since these 2 resistances are in parallel, and in parallel combination the voltage across the resistances is same, and according to Ohm's law the voltage is given by I2 R2, I times R. So here the voltage would be I2 R2, here it would be I3 R3. So by equating them you can write I2 R2 as I3 R3. So by solving these two, you will get I2 as, try to remember, you will get I2 as this resistance divided by total resistance of these two. So we will get R3 divided by R2 plus R3 times the main current I1. Okay. Similarly, I3 as, see, current in this, yes, current in this R3 resistance. So current in R3 resistance would be R2 divided by R2 plus R3 times I1. And since they are asking I3 upon I1, so bring this I1 here, you will get I3 divided by I1 as R2 divided by R2 plus R3. So R2 divided by R2 plus R3. So correct answer is B. Okay. So I'm moving to next question. Okay. Again, pause the video, solve it yourself, and then look for solution. It says one has a uniform metallic wire of 18 ohm resistance, and this wire is converted into an equilateral triangle. So suppose I have a wire of 18 ohm resistance, uniform wire of 18 ohm resistances, and after bending it, I have turned into an equilateral triangle. So all three sides will get 1/3 resistance of total. So this will be 6 ohm, this will be 6 ohm, and this branch will be 6 ohm. Now they say, what is the net resistance between any two vertices? So if I pick these two vertices as terminals A and B, can you see these two resistances are in series? These two resistances are in series. So 6 plus 6, their series combination is going to be 12, and with 12, 6 ohm is in parallel. And if with 12, 6 ohm is in parallel, the net resistance is gonna be 1 divided by 1 by 12 plus 1 by 6. Take LCM and bring this 12 times 6 divided by 12 plus 6, and you will have 4 ohm as an answer. So correct answer is A. Okay. So that was a very simple question. Let's move to next question. Again we have very simple question, and it says two equal resistances and equal resistances then when connected in series to a battery consume electrical power of 60 watt. Okay. So we have two resistances. Let's say they are R and they are connected to a battery, and the power they consume is 60 watt. So if I suppose the voltage or the EMF of battery is V, the V will be applied across the resistance, and 60 watt, as you know, power is equal to V square by R. As 60 watt is being dissipated by this two resistance, so you can say the 60 watt is dissipated by net resistance. Okay, I can write net because power is also net. So this will give you 60 equals V square divided by 2R. Okay, because as they are connected in series, the net resistance would be 2R. Okay, now they say if now the resistance are connected in parallel and then connected to the same battery. So if these resistances are connected in parallel, their parallel combination resistance would be what? R by 2. And if R by 2 is the net resistance, what is the net new power? So new power is, say, P dash, the battery is same, so V square, and then we have net resistances as R by 2. So 2 will go up. And can you see the V square by R from this equation is 2 times 60, that is 120. You put V square by R as 120, P dash would be 240 watts. And the correct answer is B. Okay, so let's move to next question. Again, this is a very interesting question, and it is based upon some symmetry. So let's read the question first. They have connected few resistances as shown, and they are asking us what is the net resistance between A and B. So actually this is based upon a symmetry which is popularly called as perpendicular bisector symmetry. Okay, so what is perpendicular bisector symmetry? When A and B are terminals, Okay, A and B are terminals. Just imagine the line AB and think of the perpendicular bisector of this line. So perpendicular bisector of this line is this dotted line, right? This dotted line. And can you see by shape the circuit on the left side of this perpendicular bisector and on the right side of this perpendicular bisector is similar. The shape of circuit on the left of, on one side of this perpendicular bisector is same as on the other side of the perpendicular bisector. But this is not enough. The corresponding resistance, is if are equal or in a constant ratio. If are equal or in a constant ratio, then we say the perpendicular bisector symmetry is there in the problem. Okay, so perpendicular bisector symmetry comes in picture when we have similar circuit on the two sides of perpendicular bisector and corresponding resistances are either equal or in a constant ratio. Can you see these two corresponding resistance has a ratio of 3/4. These two resistances again have a ratio of 3/4, and these two corresponding resistances too have a ratio of 3/4. So all corresponding resistances have a ratio of 3/4. Then we say there is symmetry in this problem, and the symmetry name is perpendicular bisector symmetry. So let me write perpendicular bisector symmetry. It is present in the circuit if corresponding resistances on two sides of perpendicular bisector, on two sides of perpendicular bisector are either equal or in a constant ratio. So this symmetry will also be present if these two resistances are equal or these two resistances must be in a constant ratio, like we have 3/4 here, a constant ratio. If this type of symmetry is present, always remember, if this type of symmetry is present in a problem, all terminals on this perpendicular bisector, are at same potential. So result of this symmetry is all points on perpendicular bisector are at same potential or equipotential, okay. All points on perpendicular bisector are equipotential. So what if we get this symmetry in some problem? If we get this symmetry in some problem, I can say here all these 3 points on this perpendicular bisector are at same potential, and as these 2 points are at same potential, there will be no current in 2 ohm resistance, or there will be no resistance in this 2 ohm resistance also. The current I1 going this side will go from this side. If current I2 is going here, it will simply go in this resistance, and say it is I2, we have I2 here, and if we have I3 here, we have I3 here, because in this branch the current cannot flow. And that proves these two resistances are in series. These two resistances are in series, though they are mechanically connected with this vertical line, but electrically there is no contact, because this contact is not sharing current with vertical branch. This horizontal current is going horizontally towards this current is going into directly this resistance, and this current is going directly into this resistance. So you can say all these three combinations are in series. So this 3 and 4 in series, this 3 and 4 in series, this 3 and 4 in series, all three becomes 7. So this is 7, this is 7, and this is 7, and we can say we have three resistances 7 ohm each connected in parallel. So the answer should be simply 7 by 3. So please remember this rule of perpendicular bisector symmetry. This may be very beneficial for you in further questions. Okay. So next we have a question on bulbs, where we are given that we have 4 identical bulbs. They are shown by these circles, and all are rated as 100 watt to 20 volts. So ratings of bulb is 220 volt, 100 watt. It means if you apply 220 volt across the bulb, it will dissipate 100 watt power. Okay. So actually in this question I have to write 220 many times, okay, because they have shown this battery also of 220 volt. So I'm assuming 220 as V0, okay, just for the simplicity of calculations. So you know, if voltage, rated voltage is 220 or V0 and rated power is 100 watt, the resistance of the ratings are used to find resistance of the bulb. So resistance of the bulb would be V0 square divided by power, which is 100 watt. This is the resistance. So each bulb has this resistance, remember, R V0 square by 100. Okay. Now you can see these three resistances, they are in parallel. So the combination of these three resistors will have an equivalent of R by 3. Okay, these three resistances are in parallel. So this combination will have an equal resistance of R by 3, and with this R by 3, this R is in series. So net is going to be R plus R by 3. Net resistance is R plus R by 3. And across the whole combination, we have applied 220 volt. So the net power can be written as net voltage in the circuit 220. We have assumed 220 as V0. So V0 square and divided by net resistance. And see, what is the net resistance? Net resistance is R plus R by 3. So we will have 3 by 4 times V0 square divided by R. And can you remember, the R was V0 square by 100. So let's place value of R as V0 square divided by 100. 100 will go into numerator. We can cancel V0 square. 300 by 4 is 75 watts. So all 4 resistances whose rated power is 100 watt each, but in this combination they all 4 together are dissipating only 75 watts. Okay, so the correct answer is A. Over to next question. Again, a very interesting and very good question. We have 2 electrical bulbs. Now we have 2 electrical bulbs, and can you see their rated voltages are same, 220, but rated powers are different. One is 25 watt bulb and one is 100 watt bulb. Okay, we have 2 watt bulb. Again, for simplicity of calculations, I can assume 220 volt as V0. So as 2 resistances have different power ratings, you can write R1 as V0 square by 25 and R2 as V0 square by 100. Okay, now they say they both are connected in series. The 2 resistances are connected in series across a 220 volt supply. So both are connected first in series across a 220 volt supply. So net power, the net power would be net voltage, which is 220. 220 we have assumed as V naught. So net power would be V naught square divided by their series combination equivalent. A series combination equivalent would be R1 plus R2. So let me place the values. R1 is V naught square by 25 plus R2 as V naught square by 100. And let's solve this. We have 2500 in the numerator and 125 in the denominator, and V naught square will cancel out. So we have 20 watt as answer. So together in series, they both dissipate 20 watt power. If they both dissipate 20 watt power, the total power should be 20 watt. So this A combination and C combination are obviously wrong because their sum is 25. Now let us see here. See, few minutes back I told you in series combination the current is same, and if current is same we can use power's formula as I square R, and if I is same we can say power is proportional to resistance. So bigger resistance will dissipate bigger power. Bigger resistance will dissipate bigger power, and I can say P1 divided by P2 as R1 divided by R2, and see R1 by R2 would be equal to 4. So P1 should be 4 times of P2, and you can see it's very clear the correct answer is D. Okay, because here we have P1 as 4 times P2. Can you see that? And their sum is 20. So this is the very right answer. Move to next question. This question is a very practical one, and it says electrical power lines. So we have few electrical power lines and they have a total resistance of 2 ohm. So total resistance of this line is 2 ohm. Okay, and they are delivering 1 kilowatt power at 220 volt. So at this end you can say the potential difference is 220 volt and the power being delivered is 1000 watt. Okay, so if power delivered is 1000 watt and we are also given voltage, I think you remember the power is also equal to V times I. So here you can find out what is the current flowing in the line, and the current flowing in the line would be I equals to P by V. So it is 1000 divided by 220. Okay, this is the current in amperes. And if this is the current flowing in these lines, okay, so power loss in these lines is going to be I square R. The R is 2 ohms. Okay, so if you put I as 1000 upon 220 squared times R as 2 ohms, you will get nearly 41 watts. So there is a power loss. There is a power loss of 41 watts nearly. Okay, and if there is a power loss of 41 watts and here we are getting 1000 watt, definitely the input power, the power input should be P input should be equal to 1000 plus 41 watts. So as they are asking us efficiency of transmission line, the efficiency should be equal to output power, which is only 1000 watts, divided by input power 1000 plus 41 multiplied by 100. That's a simple formula of efficiency of any system. Output divided by input multiplied by 100, and if you calculate it, it will nearly be equal to 96%. So the correct answer is D. I hope you are enjoying this session. I'll again say see the whole series in parts of 1 hour each, so that you stay motivated and you learn a lot. Okay, next question again. Okay, this is again a very practical question, and it says in a building. So let's first learn how many appliances like bulbs, tube lights, AC, heaters, etc. are connected in a building. You all know in our home or building, the incoming line has a potential difference of 220 volt. And every bulb, every fan, every AC, every heater, every appliance that we use is rated for 220 volt. So actually all these instruments, all these appliances are connected in parallel like this, so that every instrument gets 220 volt as voltage. That is why every bulb, every fan gets the potential difference of their rated value 220 volt, and they all perform at their fullest value, at their fullest rated power. Okay. So as they are saying, all obviously in building we are using bulbs, fans, etc. So they all must be of 220 volt. Okay, they all must be of rated voltage as 220 volt, and their powers are specified, and they are asking us the minimum fuse capacity. Obviously we use a fuse here, so that in case of a short circuit or in case of demand of excessive current, this fuse may break and all appliances can be saved. Okay, so let us see what current a bulb draws. A bulb of 45 watt, as you know, the power equals to V times I. Okay, so rated power we are given, rated voltage we are given 220, and all bulbs are getting 220, so they will all perform at rated power. So current we can find from here. So a bulb, one bulb of 45 watt will get a current of 45 divided by 220. This is current required by one bulb, and as there are 15 bulbs, the current required by 15 bulb is this. Okay, then we have 15 bulbs of 100 watt, so current required by those 15 bulbs would be 15 times 100 divided by 220. Then we have 15 small fans of 10 watt each, so plus 15 10 watt divided by 220, and then we have two heaters of 1 kilowatt. So we have two heaters of 1000 watt divided by 220. This is the net requirement of current. Okay, so this is the sum of all these currents. Okay, and you can it's very obvious to see these currents are coming from main supply where fuse is given. Okay, so if you sum this and solve it, you will get an approximate answer as 19.6 ampere. So the total current that we require, if all these instruments run at their full capacity, the total current required is 19.6 ampere. And if 19.6 ampere current is required, the 15 ampere fuse will blow, because it can work up to 15 ampere current only. The 10 ampere will blow. The 25 ampere, it is something extra. The minimum requirement out of these four options, the best option is A, because it is just close to our result 19.6 ampere. Okay, so this will be okay. Okay, so next question. Let's look for next question. Now we have another very interesting and very important combination of resistance as Wheatstone Bridge. Wheatstone Bridge has 5 resistances. 5 resistances. Okay, and but for resistance we make a quadrilateral A, B, C, D. Can you see that? 4 resistances P, Q, R and S are used to make this quadrilateral. The 5th resistance, this G, is placed in one diagonal, and other diagonal is behaving like terminals. So across other diagonal, I'll apply a battery. Okay. Remember, across other diagonal, we have to apply battery, because if you apply battery across this, it will be simply a parallel combination of three resistances. So always remember, in one diagonal, we have fifth resistance, and across other diagonal, we have to apply battery. So this is called a Wheatstone bridge. Can you see, if these two are terminals, we have a kind of perpendicular bisector symmetry, because on the left side of this perpendicular bisector and right side, the circuit has same shape. But you know, when the symmetry holds when the corresponding resistance have either equal, when corresponding resistance are either equal or in a constant ratio. So the symmetry holds when P upon Q, because these two are corresponding resistances, P upon Q, if P upon Q is equal to R divided by S, the symmetry will hold. And if symmetry holds, I think you remember, all points on this perpendicular bisector are at same potential. So if B and D are at same potential, there will not be any current in the fifth resistance G. And if there is no current in this galvanometer, you can say the P and Q are in series, R and S are in series, and this PQ and this RS combination are in parallel. Okay, so the net resistance can be written as, if asked, it will be 1 divided by 1 upon P plus Q plus 1 upon R plus S. Okay, you can also remember this condition as P by R equals Q by S. So we also remember it as either this or this ratio should be equal, or this ratio should be equal. Okay, either this ratio and this ratio should be equal, or up down, like this ratio and this ratio should be equal. If this exists in some question or some situation, there will be perpendicular bisector symmetry, and this resistance is of no use. You can think that it is not present, and these two in series, these two in series, and these two in parallel. Okay. You may be wondering why I haven't used the resistance sign in place of this fifth resistance. Actually, technically, this symbol is a resistance, but I have written G. Actually, it is also an instrument that measures or that senses the presence of current in this branch. So this is called a galvanometer. So we apply galvanometer here. It is technically, it is a resistance only, right? Technically it is a resistance, but it also has a meter, a scale on it, and if a scale shows zero value, then I can say the current in this branch is zero. And if current in this branch is zero, this Wheatstone bridge is called balanced. So always remember, if this or this condition holds, the Wheatstone bridge is called balanced. And only in balanced conditions, I can take these two in series, and then these two in parallel. So always remember this point. Okay. Sometimes the Wheatstone bridge may come in front of you in disguise. At first, you may not recognize it because they give it in different shapes. Like if you see this and assume A and C as terminals. Let us assume C at 0 potential and A as at V potential. Okay, and let's assume the potential of this point as X and this point as Y. So can you see there are mainly 4 type of potentials? Okay, if I point or place a point A here of potential V, B here, sorry, not B, C here of potential 0, X here, and Y here. Okay, just I have rearranged them like this. Can you see the R1 is between V and X? So I can place R1 between V and X. Okay, R2 between X and 0. So R2 between X and 0. Okay, R3 between V and Y. So R3 between V and Y. So between V and Y. Okay. R5 between Y and X. So we have R5 between Y and X. And R4 between 0 and Y. So R4 between 0 and Y. And now, obviously it is a Wheatstone bridge having 5 resistances. Having 5 resistances, 4 resistance we have as quadrilateral, and 5th resistance as one diagonal, and on other diagonals we have terminals. So remember this point, but this is not true. This is, we cannot say right now this is balanced. It will be balanced only when this ratio and this ratio is equal, like R1 by R2 if same as R3 by R4, then we will say it is balanced. And you can assume as if R5 is not present, and you can solve as R1, R2 in series, R3, R4 in series, and these two in parallel. You can simply forget about R5 and move forward. So let us solve a few questions based on the Wheatstone bridge. So in this case, we are given in the Wheatstone bridge as shown in the figure, P and Q are approximately equal. They are not equal actually, they are approximately equal. And we have a switch here K2, we have a switch here K2, and we have a switch here K1. Okay, actually when K1 and K2 are closed, this Wheatstone bridge operates. Okay, in the next slide it says when R is 400, okay, right, when R is 400, let me read the question. The bridge is balanced on interchanging, well, okay, let me first write when R is 400, bridge is balanced. So listen to this line very carefully. When R is 400, bridge is balanced. Okay, so if bridge is balanced, I can always apply this ratio is same as this ratio. So let me write P by Q equals R as 400 divided by X. Okay, this is equation number 1. And the next line they say on interchanging P and Q. So I have placed Q here and P there. So imagine Q here and P there. On interchanging P and Q, the value of R for which balance occurs is 405. So R becomes 405 and then balance conditions are again established. So if P and Q are interchanged, I can write Q divided by P equals to 405 divided by X. That is equation number 2. Okay, now simply multiply these two equations, LHS by LHS, RHS by RHS. So on multiplying LHS by LHS, okay, or you can do a very simple thing, just flip this equation, okay, and put the value of P and Q at this point. Okay, so if you see P upon Q from this equation, it will be X upon 405, X upon 405 equals 400 upon X, 400 upon X. So from here you can say X is equal to square root of 400 times 405. So actually X is geometric mean of these two values 400 and 405. Okay, so if you calculate this, you will get nearly answer as 402.5 ohms. So correct answer is obviously D. Okay, so let's move to next question. In this question again they are saying we have 4 resistances, 15 ohm, 12 ohm, 4 ohm, 10 ohm respectively in cyclic order to form a Wheatstone network. Okay, let me first draw this. We have a Wheatstone network like this. Okay, first is 15 ohm. The second is 12 ohm in cyclic order. Don't forget 4 ohm and 10 ohm. We must have a fifth resistance also. Okay, let it be small r. Now they say, what is the resistance to be connected in parallel with 10 ohm for this Wheatstone bridge to be balanced? So if I connect a resistance X in parallel with 10 ohm, we have to find the value of X such that this Wheatstone bridge is balanced. So what is the condition of balanced? If it is balanced, this ratio will be same as this ratio, and this resistance will have no electrical influence. It will have no electrical value because current in this resistance would be 0. So let me just write the condition. This ratio as 15 by 12 equals to this ratio. But we have a combination of 10 and X in parallel at the place of 10 ohm. So in the place of 10, we have a combination of 10 and X. So 10 and X combination becomes 10X upon 10 plus X divided by 4. Let's solve it. 4 3s are 12, 3 5s are 15. So now I have 5 2s are 10. So we have 10 plus X equals to 2X, and then we have X equals 10 ohm. So simply I have to use 10 ohm resistance in parallel to 10 ohm resistance to make this Wheatstone bridge balanced. Okay, so let's move to next question again. Okay, a similar kind of question, because here also we have connected some resistance in parallel with 100 ohm. Let's see what the question is. If this question says the given Wheatstone bridge is showing no deflection in the galvanometer between point, okay, calculate the value of R. Answer is again very simple. If there is no deflection here, it is balanced, and if it is balanced, this ratio must be same as this ratio. Remember, so this ratio, the first ratio is 100 divided by, at the place of this 100, I have a combination of 100 and R. So the combination of 100 R gives 100 R divided by 100 plus R equals, the lower ratio is 200 divided by 40. Okay, let's cancel few things. 0 0 0 0. Okay, 2 and one more 0. I have 100 plus R divided by 10 R on LHS and 1 by 2 on RHS. So cancelling this, I have 100 plus R as 5R. So R becomes 100 upon 4, that is 25 ohms. So correct answer is A. I think this question is too easy for you. Always pause the video. While seeing this video, always pause the video as you look at the new question and solve it yourself. That will help you a lot, because if you solve it yourself, there will be no need to revise the whole video at home. Okay, so over to next question. So now in this question, they say we have a wire of resistance 0.1 ohm per centimeter. Means we have a wire, okay, and 1 centimeter of the wire has resistance 0.1 ohm. 10 centimeter will have a resistance of 1 ohm, and 1 meter means 100 centimeter will have a resistance of 10 ohm. Okay, so actually we have a wire, and with that wire we have to make a square ABCD of side 10 centimeter. So we made a square A, B, C, D, and every side is 10 centimeter. As 1 centimeter has resistance 0.1 ohm, so 10 centimeter will have a resistance of 1 ohm. So each side has a resistance of 1 ohm. Okay. A similar wire is connected between the corners B and D. Okay. A similar wire is connected between the corners B and D. Right. Okay. To form the diagonal BD, find the effective resistance of the combination between corners A and C. So see, can you see between A and C, it is a Wheatstone bridge. And also, as you can see, this ratio is 1 and this ratio is 1. This is a balanced Wheatstone bridge. And if it is a balanced Wheatstone bridge, you can simply ignore this resistance as current will not pass in this. And again, these two in series, these two in series. So in series it becomes 2, and 2 and 2 in parallel it becomes 1 ohm. So I think they are asking if 2 volt battery of negligible internal resistance is connected across A and C, calculate total power dissipated and also the effective resistance. So effective resistance is 1 ohm, and if effective resistance is 1 ohm, answer can be A or B. Okay, okay. And now if effective resistance is 1 ohm, imagine the effective resistance is 1 ohm and I am using a battery of EMF 2 volt, ideal battery of EMF 2 volt. The power is going to be V square by R. V square is 4, R is 1. So V square by R is simply 4 watt. So correct answer is B. Okay. So I think that was a easy question for you. Let's move to few more concepts of this chapter. Okay. So we, after grouping of resistances, we have combination of cells, and if we group cells side by side, it becomes series combination of cell. So we have case 1 as series combination of cells. Okay. In this combination, can you see few batteries are connected. This dotted line means we have n cells. First battery has EMF E1 internal resistance R1, second has E2 R2, and nth has En Rn. So if this whole setup or this combination of these batteries is to be replaced by a single battery, okay, that battery would be called equivalent battery of this combination if it works the same way as this used to be working. Okay. So if this equivalent battery has EMF as E net and internal resistance as R net, let me tell you how to calculate the E net and R net. I think you remember in real batteries, the terminal voltage across the battery is equal to EMF when there is no current in it. Do you remember? Yes. If you do not send any current in the battery, the terminal voltage is equal to EMF, because the terminal voltage is given by V equals to E minus IR in case of discharging battery plus IR in case of charging battery. But if there is no current, V will be equal to E. So terminal voltage can be called as net EMF if there is no current going in the combination. So just don't send any current. And if you do not send any current, assume this voltage as 0 and start from here to here. Okay, we are trying to find potential difference simply, and I know the potential difference would be equal to EMF because there is no current, right? So okay, let's start from here. If the potential of this point is 0, in resistance there will be no potential difference because current is 0. So if we have 0 here, we have En here. Move further, we have En minus 1 added, or at this point, if you move from here to here, E2 will be added, and if you move from here to here, E1 will be added, right? Okay, E1 will be added. Or I can let me repeat it in a different manner. Let's say the terminal voltage is V, because I have assumed this voltage as 0 and this potential as V, and let's write open loop KVL from here to here. Okay, so let's write V. I'll start, because I'm writing open loop KVL, I'll start with V. Then minus E1, minus E2, minus E3, etc. And I'll reach at En. And it is equal to 0, the potential of this point. And now you know V equals to E1 plus E2 plus E3 plus E4 up to En. So obviously V is equal to effective EMF. So effective EMF becomes E1 plus E2 plus E3 plus E4 up to En. Remember? And the net resistance, the net internal resistance will be given by a single internal resistance, and that internal resistance would be the equivalent combination of resistance if you ignore the batteries. So if you ignore the batteries, you see R1, R2, R3, Rn are all in series. So equivalent internal resistance will be given as R1 plus R2 plus R3 up to Rn. So always remember, in the series combination it is very simple. Simply E net is E1 plus E2 plus E3 means sum of all EMFs, and R net as sum of all internal resistance. That's very simple to remember. Case 2. Case 2 is just a case of the first one. If all batteries have same EMF. So if all batteries have same EMF, the net EMF would be E1 plus E2 plus E3 up to En, and the sum would be N times E, because there are N batteries and all batteries have same EMF E. So equivalent batteries EMF would be NE, right? And simply the R net would be N times R. So I think the idea is very simple. It is just an extension of first case. Okay. So if you anyway see large number of batteries, large number of identical batteries connected in series, and all have same polarity, all are positive towards left or all are positive towards right, then effective EMF would be N times E, the number of cells times EMF of one battery, and resistance, internal resistance, as number of cells times internal resistance of one battery. Okay. What if few batteries are in opposite polarity? Can you see here, every battery is positive terminal is towards left, every battery is positive terminal is towards left, only this E2 is towards right. So if this E2 is towards right, when you write KVL, assume potential at this point as 0, assume potential at this point as V. When you start writing KVL from V, I'll write V minus E1 but plus E2. I think you can see from here to here the potential is decreasing, but from here to here potential is increasing. Again minus E3, because I'm assuming only E2 is flipped, En equals 0. So you will have the effective EMF as this, because E2 is negative here, E2 is positive here, it will be negative on the right hand side. So always remember, if all batteries have same polarity and few are reversed, the reversed cells will come with negative EMF. Okay, will come with negative EMF. Okay, and this is equal to, this is actually the equivalent EMF of the battery, and on R net there is no effect of flipping the battery, because when we calculate R net we ignore the batteries and simply take their internal resistance combination. So if you are ignoring the batteries, polarities has no significance. Okay, and the net resistance, net internal resistance would be R1 plus R2 plus R3 up to Rn. Okay, so remember these points. Okay, so before moving to questions, let us also solve, or let us also study the parallel combination of batteries. So if few batteries, let's say we have few batteries, let's say n number of batteries, and these are connected in parallel. If these are connected in parallel, I am not deriving the relation. Actually, there exists a Millman's theorem. Millman's theorem. And according to Millman's theorem, if we have parallel combination of batteries like this, then equivalent EMF is given by, try to remember, E1 by R1 plus E2, EMF by internal resistance, EMF by internal resistance. So sum of ratio of EMF and internal resistance. Okay, E1 by R1 plus E2 by R2 plus E3 by R3 up to covering all cells, divided by 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 up to all cells. Okay. So this numerator you can write as summation of E by R. Okay, summation of E by R. And this denominator, according to parallel combination of resistance formula, you can write it as 1 by R net. Assuming all resistances in parallel, assuming all internal resistances in parallel, you can assume this as 1 by R net of all resistance. Okay, so 1 by R net will go up and it becomes the numerator multiplied by R net. So always remember this formula, E net is summation of E by R, summation of all E by R multiplied by R net. While calculating R net, just ignore the batteries and you will see all internal resistances are connected in parallel. So R net will be their parallel combination resistance. Okay, remember this. It is written here also. And one more thing, if you see any one battery is flipped, if any one battery is flipped, suppose E2 is flipped, give E2 a negative sign in this summation. So the batteries which are flipped, which have reverse polarities, always give them a negative sign. This you have to remember. So let us see what we have next. We have a mixed combination. So in this mixed combination, you can assume we have M rows. We have M rows of cells, and in each row we have N cells. So we have a mixed combination of large number of batteries, large identical number of batteries placed in similar polarities. Okay, but we have taken M rows of one row having N cell each. So we have a total of N equals to M times N cells. If this combination has to be converted into a single equivalent battery, the idea is simple. Just think of this row first. It has N cells, so this row's equivalent EMF becomes NE and equivalent resistance becomes NR. Okay, so this row can be converted as one battery having NE EMF and NR resistance, and now you can assume you have M cells, each cell is of NE EMF and NR internal resistance. So now I can use Millman's theorem, and if I use Millman's theorem, the E net is going to be, let us see what is E net. E net is summation of EI by RI. Okay, so it is summation of C. Every battery has NE EMF and every battery has NR resistance. So summation of M terms, this we should multiply as the net resistance, and in net resistance we have M resistances, M NR resistances in parallel. So if we have M NR resistances in parallel, then R net is going to be NR divided by M. Okay, as these N are cancelled, Okay, and as there are m terms, can you see there are m cells, m rows. So in parallel there were m cells. So sum of m terms would be me divided by r times nr divided by m. M got cancelled, r got cancelled, and E net is simply Ne. The idea is simple. The idea says if you have m rows of identical cells in same polarity, we do not get any advantage in effective resistance. The effective resistance is same. The effective resistance is same. But we have an advantage of internal resistance, because the equivalent internal resistance would now be NR by M. NR by M. So by taking multiple rows, I can reduce the internal resistance of the battery, and the battery would be as close as the ideal one. Okay. Again, in this question they are asking what is E net and R net. Let's repeat it again. As you can see, it is a parallel combination of n cells. Suppose there are n, or let's say m cells. We have m cells, and each cell has EMF E and internal resistance R. So by applying Millman's theorem, E net is going to be summation of E by R, and you know this summation has m terms, and this multiplied by R net. So you can see in R net we have n resistances in parallel, n identical resistances in parallel. So R net becomes not n, m, R by m. This is R net, and in this we have m terms. So we have m E by R times R by m. So answer is E. And I just told you, if we take large number of cells in parallel, there is no advantage of EMF. The EMF would remain same. Okay, but internal resistance is reduced because R net here becomes R by M. Okay, so that was a combination of cells. Okay, and let us now solve few problems, very important problems, okay, based upon this combination of cells. Okay, so now we have a battery consists of a variable number of identical cells. Means cells are identical, but number of cells is variable. We may have a 10 cell battery, we may have a 100 cell battery, I don't know, but there are n cells, okay, which are connected in series, and all batteries have R internal resistance. So let us draw. These are batteries. Okay, suppose each battery has E as EMF and R as internal resistance, and we have n cells. This is the combination, series combination of n cells having EMF E, we have assumed E, and R as internal resistance. Now they are saying their terminals, their ends are short circuited. So if their ends are short circuited, yes, we have done this. And if we have done this, the current I is measured, and we have to tell them which is the perfect graph for I versus N, how the I will vary if we increase or decrease the number of cells. Okay, let's find current. As you know, this is a one loop problem. This is a one loop problem, and in one loop I already told you that current is equal to net EMF upon net resistance. And as the net EMF in this loop is N times E, as we studied in the case of series combination of cells. And as we have R resistances in series, the net resistance is NR. So N got cancelled and I is equal to E by R. So the idea is, whatever be the number of cells, the current will be constant, and the correct graph is this, because I here is not depending upon n. You increase the number of cells, but the I graph is horizontal. The value is equal to E divided by R. Okay. So over to next question. Okay. Here we have two batteries of EMF 12 volt and 13 volt in parallel across a load resistance of 10 ohm, and internal resistance of two batteries are 1 ohm and 2 ohm. The voltage across the load lies between. Okay, so first let me draw. We have two batteries in parallel. One has 12 volt, other has 13 volt, 1 ohm, 2 ohm, and this is connected to a load resistance. How much load resistance we have? 10. As we have studied parallel combination of batteries, so let us convert these two batteries into single one. Okay, and if we convert these two batteries into single one, they are in parallel, Millman theorem will be applied, and Millman theorem says the net EMF will be summation of E by R. Remember, summation of E by R. So summation of 12 by 1 plus 13 by 2 times R net. R net means the effective resistance of these two, internal resistance. So they are in parallel, 1 and 2, and 1 and 2 effective becomes 2 by 3. So this is the E net. Okay, and if this is the E net, let me calculate the value. It is 12, it is 6.5. So we have 18.5, right? 18.5 multiplied by 2. So it will be 37 divided by 3, right? 37 divided by 3. So this is the E net. R net is obviously 2 by 3. And if R net is 2 by 3, the internal resistance is 2 by 3. Obviously, the current in the circuit becomes E net, that is 37 by 3 divided by net resistance, and net resistance is 10 plus 2 by 3. Okay, 10 plus 2 by 3. So just find current, and current would be 37 divided by, take LCM and cancel 3, we have 32. 37 by 32. Okay, 37 by 32. This is the current flowing from the equivalent battery into this circuit. And if this is the current, the potential difference across this 10 ohm would be I times R according to Ohm's law. So the answer should be I times R. I times R, 37 by 32 multiplied by 10 means 37 into 10 divided by 32. And after calculating this, you will see the answer nearly as 11.56 volt. So it is between these two limits. So correct answer is D. Okay, so that was a very simple question. Okay, and let's move to next one. Again they say in the circuit shown, the potential difference between A and B. Simply apply Millman theorem, you will get answer. Let us apply Millman theorem. E net is going to be, first take these three as three batteries in parallel, and you will have 1 by 1, because we have to sum E by R. We have to sum all E by R. Okay, so 1 by 1 plus 2 by 1 plus 3 by 1 and multiplied by the net resistance. So what is the net resistance? 1, 1, 1. In parallel, we have net resistance as 1 by 3. So it is 6 by 3 and answer is 2 volt. Okay, so E net, the effective EMF of this cell is 2 volt and R net as 1 by 3. So I can replace this circuit as 5 ohm, then this battery as 2 volt, resistance as 1 by 3 ohm, and then we have 10 ohm. But as you can see, there is no current here or here. So in this system, there is no current. Potential difference, the net potential difference across this and this would be 0. And the only potential difference across this combination would be EMF of the battery. So answer is 2 volt. Correct answer is B, because there is no current flowing from A to B. And if there is no current flowing from A to B, all resistances will have no current and no potential difference. Okay. So let me move to next question. If you are tired, please take a rest, take a break, pause the video and see it again. Okay. So now we have n sources of n batteries. Actually, we have n batteries with different EMFs are connected as shown in figure. Okay. So in this, can you see all batteries are in same order? All polarities are clockwise. Okay. Then they say EMF of the source are proportional to their internal resistances. EMF of the source are proportional to their internal resistances. Means if some battery has EMF as E1, E1 would be proportional to their internal resistance R1. So I can write E1 as KR1, E2 as KR2, because all EMFs are proportional to resistance. So proportionality constant is same and I've assumed it to be K. Okay. And if this is the case, let me find the current in this loop. Okay. The current in this loop is going to be total EMF upon total resistance. So we have E1 plus E2 plus divided by R1 plus R2 plus R3, etc. Now replace E1 by KR1, E2 by KR2 and take K common, and you will see the bracket R1 plus R2 plus R3 in both numerator and denominator. Let's cancel it and answer would be K. So here current is equal to K. Okay. Now they are saying, actually they have taken proportionality constant as alpha. Okay, but I have taken K. So you can think alpha and K are the same. Okay, assume alpha and K are the same. Actually alpha is not required for the solution. Okay. The connecting wire resistance is negligible. Okay, I have assumed it to be 0. The potential difference between point A and B dividing circuit in n and n minus 1. Suppose between A and B, on one side we have n resistances and on the other side we have n minus n resistances. We have to find potential between A and B. By looking at the polarity, I can be sure that current will be in this direction, I. So let me calculate potential difference across any one battery. Okay, let me calculate potential difference across any one battery. So pick any battery. Let's say pick a ith battery. Take ith battery. Okay. If you take an ith battery, the potential difference across ith battery would be ith battery's EMF minus I times ith battery's internal resistance as Ri. But EMF of ith battery will be, according to this relation, it will be equal to K times Ri. So I can write it again as EI as K times Ri and I as K. So I can write I as K times Ri. These two cancels and become 0. What it says? It says you pick any battery and the potential difference across any battery would be 0. And if potential difference across any battery is 0, you make any combination n or n minus 1, it doesn't matter. If potential difference across any battery is 0, potential between any 2 points will be 0. The correct answer is A. Okay, the correct answer is A. So let's move towards next question. As we have studied many quantities in this chapter like electric current, potential difference, power, etc. So they need to be measured, and measurement of these quantities is another very important aspect of this chapter. So now we will learn how to measure current, voltage and resistances. Okay. So the first and basic instrument is galvanometer. Galvanometer can sense the presence of current or potential difference in a circuit. Okay, but it has its limitations, but it is the first basic instrument. So let us start with this. Okay. Actually, the working of galvanometer I'll explain in the chapter of magnetism, because its working is based upon principle of magnetism. But here I can tell you the galvanometer has a resistance coil, a very thin light resistance coil in it, okay, that moves in magnetic field when a current is passed in it. So whatever current we have to measure, we pass in this coil, in this resistance coil of galvanometer, and according to that current the coil moves, and we measure this movement. And since this movement or this deflection is proportional to the current going in the coil, measurement of this current is possible. Okay. So this is the symbol for galvanometer, and as it has a resistance coil, I can say the resistance of galvanometer is R. Okay. I can send many currents in it, but the maximum current above which the current should not be given to this galvanometer is Ig. So Ig is the maximum limit. Okay. If you give current more than Ig, it may burn or it may not function properly. So Ig is the maximum deflection current. So when you send Ig, the pointer of deflection goes to maximum value. We also say Ig as maximum deflection current. Okay. And if you multiply Ig by R, you get potential difference across galvanometer. This is called Vg. And obviously, when Vg is the potential difference in the galvanometer, of course the current is Ig. So if you use galvanometer as a voltmeter, on a scale you will see maximum deflection of the pointer. So Ig and Vg are called maximum deflection current and maximum deflection voltage. Sorry, it is not current, it is voltage. Okay. So remember, Ig is the maximum current that we can send safely in galvanometer, and when we send Ig, the pointer of galvanometer goes to maximum value. Okay. So we should not ever send a current more than Ig in galvanometer. But the limitation is this: it can measure a current up to Ig, it can measure voltages up to only Vg, but these values of Ig and Vg are very small. Usually the Vg is of 1 or 2 or 5 volts, not more than that, and Ig is of values say few milliamperes. Ig is in few milliamperes only. So you cannot measure big currents and big voltages if you want by using galvanometer. That is the limitation. The value of Ig is very small as compared to the current we wish to measure, and Vg is very small as compared to the voltages we want to measure. So fortunately, by doing some slight simple modification in galvanometer, we can make good current measuring and voltage measuring instruments. So current measuring instruments are called ammeter. Remember, they can measure big currents. Ammeters can measure big currents like 10 ampere, 100 ampere. Ammeters can measure. They are not some different instruments. They are made by modifying the galvanometer a little. So they are made by modifying galvanometer. Okay. They are connected in series. If you want to measure current, you have to connect ammeter in series to the branch in which we have to measure current. Obviously, then only the measured current will go into ammeter and ammeter will measure it, obviously. So yeah, the ammeters are connected in series. Okay. And Again, ideal is as ammeters are being connected in series, if ammeters have some resistance, it will change the circuit. It will change the original circuit, and the current we want to measure will actually change because of the resistance of ammeter. So ideal ammeter must have zero resistance. Ideal ammeters must have zero resistance such that when they are added in series, the circuit has no electrical change, okay, of current. So ideal ammeters have zero resistance, okay. So how we make an ammeter? Listen carefully. We have a galvanometer. Suppose the galvanometer's resistance is Rg, okay, and it can measure a current up to Ig only, okay. But I want to measure a big current I, and I is very big as compared to Ig. If I send this current into galvanometer, galvanometer's coil will definitely burn and it will not function. It will burn. So what we do, we add a parallel resistance. This parallel resistance is popularly known as shunt, or it's called S. It is called shunt. And the function of shunt is, when you send big currents, it sends only Ig, because here Ig is permitted. It sends only Ig in galvanometer, and the remaining current is bypassed through shunt. So I minus Ig, the remaining current is bypassed through shunt. You don't have to remember any formula. Just look carefully. These two resistances Rg and S, they are in parallel. And if they are in parallel, the voltages should be same. Voltage is equal to I times R. So in above branch, we have Ig times Rg as voltage. And in lower branch, we have I minus Ig times S as voltage. Just remember this rule. Make potential, always remember, send whatever current you want to measure. Only Ig will go into galvanometer and the remaining current will be bypassed through shunt, and make the potential here equal to potential here. I times R equals to I times R. This is the formula from which you can measure the value of shunt required, okay. This combination of galvanometer plus shunt is called ammeter of range I, because it can measure up to I, and this is symbolized as A. Okay. As the resistance of ammeter is parallel combination of Rg and S, resistance of ammeter becomes Rg S divided by S plus Rg. Okay, S plus Rg. Right. And since S is very small, actually S is very small as compared to Rg, S is very small as compared to Rg, so you can ignore the S plus Rg as simply Rg, because S is very small as compared to Rg. So Rg and S plus Rg are almost equal. So this becomes almost equal to S. So in real cases, in practical cases, if we talk about a real ammeter, it doesn't have zero resistance. Its resistance, the resistance of an ammeter is almost equal to its shunt resistance, which too is very less, but it will create some error. Okay, the real ammeters create some error. Ideal ammeters do not have any error in the circuit. And always, and remember this formula. This formula is very important. Just remember Ig, Rg. And if you do not want to remember, just remember this circuit. We have a galvanometer and we have a shunt resistance. Means we have a parallel resistance. We are sending Ig in the galvanometer because that is the current should be sent in galvanometer, and the remaining I minus Ig must be bypassed through shunt, and IR equals to I times R. That's it. Let's learn how to convert a galvanometer into a voltmeter. It's again a very simple science. So voltmeters, they can measure big voltages, and they are again made by modifying galvanometers. Okay. They are connected in parallel in the circuit across the points whose potential difference is to be measured. Okay. And ideal voltmeters have infinite resistance. Okay. Ideal voltmeters have infinite resistances. So how to make a voltmeter? Suppose we have a galvanometer here and its resistance is Rg. Okay. And obviously when we send, I cannot send current more than Ig here. So let's send Ig current only. And across this, the voltage is Vg. But I want to measure a big voltage. I want to apply a very big voltage, say V, across voltmeter. So what I will do, I'll add a resistance in series. Let's say a resistance R in series. Okay. So if V is applied across this combination, Vg will be across galvanometer, and the remaining V minus Vg is across this new resistance R. Okay. And as they are in series, current is common in them. And if current is common in them, you can write Ig as Vg by Rg, or V minus Vg, the potential difference across R, divided by R. And by using this, just do not try to remember the formula, just you have to make equal to I same in all elements, and it becomes a voltmeter. This galvanometer in series with a resistance is called voltmeter, and its symbol is this. If we have to measure potential difference between 2 points of a circuit, let's say A and B, we should connect this voltmeter across those points or in parallel with those points A and B. But if we do not want to change the circuit, if we wish the circuit remains same as before, the voltmeter should not draw any current in it. The voltmeter should not draw any current in it, and this branch will not draw any current if the resistance of this branch is infinity. So ideal voltmeters must have infinite resistances. That is the simple formula. That is the simple funda. The ideal voltmeters must have infinite resistance, but real voltmeters do not have infinite resistance. They have resistance of voltmeter as Rg plus R. Actually, this resistance, also called multiplier resistance, is much bigger than Rg. So you can approximate that resistance of voltmeter is nearly same as R. Okay. So remember this, ideal ammeter has all zero resistance and ideal voltmeter has infinite resistance. But real voltmeters and ammeters have some resistances. Real voltmeters have big resistance, obviously big resistance, but not infinity. Real ammeters have a small resistance, nearly equal to shunt resistance, but not zero. Okay. So let us learn how to solve the questions based upon galvanometer and ammeter. Okay. So this is NEET 19 question, and remember, whenever they say and they don't give you any clue about the ideal or non-ideal nature of ammeters or voltmeters, assume them to be ideal in very simple question. Okay. Okay. So in the circuit shown below, I think the question, in the question it should be written that in the circuit shown below, the readings of ideal voltmeters and ammeters will be. There should be a word ideal, but they are not using it. They are assuming that you will automatically assume they are ideal. Okay. So by assuming them to be ideal, okay, we have to compare the readings of voltmeter and ammeter in circuit 1 and in circuit 2. So if this voltmeter is ideal, its resistance is infinity, so it will not draw any current, and current from here will go to here, here, here. This ammeter is also ideal, so its resistance is 0, so the current will go here. So the current would be EMF divided by, this is the only resistance in the circuit. This is the only resistance in the circuit. So current will be 10 by 10, that is 1 ampere. So obviously the ammeter will read 1 ampere. And if ammeter will read at 1 ampere, let's see what voltmeter is reading. The voltage across this 10 ohm is 10 ohm times 1 ampere, that is 10 ohm. So V1 is also reading 10 ohm, because voltmeter reads the voltage across it, and the voltage across V1 is simply voltage across 10 ohm, and the voltage in 10 ohm is 10 volt. So V1 here is 10 volt, A1 here is 1 ampere. Let's look at the second circuit. In the second circuit, they are using ideal voltmeter V2 along with a 10 ohm resistance in series. But if we have an ideal voltmeter, its resistance is infinity, adding 10 more ohms will not affect anything. The net resistance of this branch is going to be infinity. Okay, and if resistance of this branch is infinity again, the current here in this branch is 0, no current. So again, current from battery goes directly to 10 ohm and then through an ideal ammeter. Again, current is 1 ampere, so ammeter read 1 ampere, and voltmeter 2 will read 10 volt because the voltage across 10 ohm is 10 volt, resistance times current, and voltage across this 10 ohm is 0. Why? Because there is no current in this 10 ohm. Okay, there is no current in this 10 ohm, so you can say voltage across this V2 is simply this 10 volt. So we see the voltmeters and ammeters readings are same in the two sockets, so the correct answer is C. Okay, let's move to next question. Here we have a galvanometer with a coil resistance of 100 ohm, means Rg is 100. Okay, let's write Rg is 100 ohm. It gives a full scale deflection where a current of 1 milliampere is passed. So obviously by description you can say Ig is 1 milliampere. It is full scale deflection current. The value of resistance which can convert this galvanometer into an ammeter, giving a full scale deflection for 10 ampere. So we have to measure 10 ampere and we have to make an ammeter. Always remember, when you make an ammeter, you put a shunt resistance in parallel with galvanometer. Let's assume this shunt is S. This resistance is R, 100 ohm. The current we want to measure is 10 ampere. Always remember the full functioning. We have to measure 10 ampere, but we cannot send more than 1 milliampere here. So remaining 10 ampere minus 1 milliampere will go into shunt. And as these two are in parallel, make I1 R1 equal to I2 R2. That's simple. I1 R1. So 1 milliampere multiplied by 100 is 0.1. 1 milliampere multiplied by 100 is equals to 0.1 equals to 10 ampere minus 1 milliampere. See, 10 ampere minus 1 milliampere is nearly 10 ampere. Is nearly 10 or multiplied by S. So we have S as nearly 0.01 ohms, and the correct answer is D. So that was a very simple question if you follow the theory. Okay, next question again, and asked twice. Actually, when they asked a second time in 20 after 17, they changed few numerical values only. Otherwise, the two questions were identical. So when a current of 5 ampere is passed, 5 milliampere is passed, galvanometer having a coil resistance of 15 ohm shows full scale deflection. So by these two lines I can say Ig equals 5 milliampere and Rg as 15 ohm. The value of resistance to be put in series with a galvanometer to convert it into a voltmeter of range 0 to 10 volt. So we have to measure a maximum of 10 volt. Always remember, with galvanometer we add a resistance and it becomes a voltmeter. But remember, we have to measure 10 volt. Okay, but across galvanometer, the voltage should not exceed Vg. And what is Vg? Vg is IgRg. Vg is IgRg. Okay, so or you can say what current I should send in? Ig. What current I should send in? Ig. Okay. What is the voltage here? The voltage here is Vg, and the voltage here in resistance it is plus minus V minus Vg. Or we can simply say the voltage across the combination is 10 volt. So if voltage across the combination is 10 volt and current is in the combination is Ig, so I can write current as total voltage divided by R net, or Ig as 5 times 10 to the power minus 3 as 10 divided by what is R net? R net is Rg plus R, means 15 plus R. 15 plus R. Let's see what is the value. So we have 15 plus R as 2000. Okay. So R will be 2000 minus 15, and 2000 minus 15 is B. 1985 times 10 to the power 3. Sorry, it is ohms. Okay, it is ohms. So let's move to next question. It's a very basic question. Okay, simply Ohm's law will help here, but they are using voltmeter, so that's why I took it here. In the given circuit, they say R1, they have set values of R1 400, R3 100, R4 500. So it is 400 ohm, it is 100 ohm, it is 500 ohm. And reading of voltmeter across R4 is 5 volt. Means if you apply a voltmeter here, the reading is 5 volt. Or simply you can say across R4 the voltage is 5 volt. If across R4 the voltage is let me write it again. It was 100 ohm and it was 500 ohm, and across R4 the voltage is 5. So current in R4 is, let's write current in R4, let's say I1, let's say it is I1. So I1 would be voltage 5 divided by 500, and we have 0.01 ampere. Okay. If current in R4 is I1, current in I3 should be I1 again because they are in series. And if current in R3 is I1 0.01, multiply this current by R3 100 ohm, you will get 1 volt. So here we have voltage as 1 volt, here we have voltage as 5 volt. So across this we have voltage as 6 volt. No, not 15, it is simply 5 volt. Okay, so we have 6 volt across these 2 points. 6 volt. Okay, so if we have 6 volt across these 2 points, we have 6 volt across these 2 points also because they are in parallel, 6 volt. And here we have 18 volt ideal battery, here is 6 volt, remaining will be across R1. So R1, across R1 we have 12 volt because 18 minus 6 is 12. If we have 12 volt here, the current here, let's say I would be 12 divided by 400, and it is equal to 0.03. ampere. So 0.03 is going here, out of which 0.01 is going above. So current here will be 0.02 ampere. So now we know what is the current in R2. Okay, and if we know current in R2, if we know voltage across R2, the R2 should be the voltage 6 volt divided by current 0.02 ampere, and the answer is 300 ohms. So correct answer is C. So that again was a very simple question. Okay, so let's move to next question. Again, I am saying again and again, solve these questions yourself first and then look for solution. Okay. Again, we have a very interesting question. So they say the actual value of this resistance in the figure is 30 ohm. We have R as 30 ohm. Okay, we have R as 30 ohm. But if we measure the ammeter reading and the voltmeter reading, if we measure the ammeter reading and voltmeter reading, the readings are V and I. Okay, the readings are V and I. And if we calculate the value of R as V upon I, if we calculate value of R as V upon I, we are getting the readings of resistance R as 5% less. Why 5% less? Because suppose if we have current I here, and obviously suppose the reading, why the reading is less? Obviously we must have been using real or practical ammeters and voltmeters here, because if they would have been ideal ones, the readings cannot differ than actual. Okay, so obviously we are using practical voltmeters and ammeters, and they have their resistances. So this I is going in an ammeter, that's okay, but this will split in two parts, and let's say I1 is going in R and remaining I minus I1 is going in voltage. The voltmeter, and the voltmeter is connected across R, so voltmeter must be showing the actual value of potential difference across R. Okay, so if we divide the voltage across resistance divided by actual current in R, like I1, I would have got the exact resistance, which is 30 ohm. Okay, but since I am not using the correct current, I am using the wrong current. I should use I1, but I am using I, a bigger current than I. Obviously, if current is bigger, the value of resistance should be smaller. Value of resistance obtained should be smaller. So as we are using V divided by I am getting the 5% less result. See, 30 is 10% is 3 ohm. So 5% should be 1.5 ohm, right? So 5% less means 30 minus 1.5, that is 28.5 ohm. This is the value. And if you divide these two accordingly, you divide equation 2 from equation 1, you will get I1 upon I2, I1 upon I as 28.5 divided by 30. Okay, 28.5 divided by 30. Now remember the current divider rule I told you in some problem maybe an hour ago. If this is the main current, okay, and it is being split into two resistance, let's say R and voltmeter resistance as X. Suppose voltmeter resistance as X. Current in this I1 would be given by this resistance X divided by total resistance, means X divided by R plus X times the original current I. As you know, I1 by I is this. I can write, bring this I here, you will get 28.5 divided by 30 equals X upon R, which is 30 plus x and solve this equation to get the value of x, and you will get the correct answer as 570 ohms. So this is the value of voltmeter's resistance. Okay, so let's move to next question. Here we have again a galvanometer of resistance 20 ohms, 30 divisions on both sides, means this galvanometer has 0 in the middle and 30 division on right side and 30 division on left side. Obviously pointer stays at 0 and in any direction it can go up to maximum of 30 divisions. Its figure of merit is 0.005 ampere per division. Actually figure of merit means, or simply you just concentrate on unit. The unit will tell you that 0.005 amperes are required for the pointer to move by one division. So if 0.005 amperes are required for the pointer to move by one division, multiplied by 30, this much current will be required to move the pointer by 30 division, and since there are 30 divisions only, this current is maximum deflection current. Rewind this again if you don't get it in first shot. Okay, so IG becomes 0.15. Please check the values. IG is 0.15 ampere. And when you know IG, I think the problem is very simple for you. They are saying the resistance of galvanometer is 20 ohm, and what should be the resistance that should be connected in series so that it can be made a voltmeter that can measure up to 15 volt. So in the galvanometer of 20 ohm resistance, we should add a series resistance R, and across this combination I should apply 15 volt. So current in this should be IG. So I can write IG as 0.15 equals to the total voltage 15 divided by 20 plus R. Okay, 20 plus R. So now you will see 20 plus R as 100. So R will be 80 ohms. Okay, so I think that's a very good question. Okay, as in 19, and now we can move to next one. Here we have two resistances, 400 ohm, 800 ohm, connected in series across a 6 volt battery. Let's draw. We have 800 ohm, we have 400 ohm, 800 ohm, and they are connected across a 6 volt battery. Okay. The potential difference measured by a voltmeter of 10 kilo ohm resistance across 400 ohm. So they have connected a voltmeter across 400 ohm, and the voltmeter resistance is not infinity. So it is a real voltmeter, a practical voltmeter, I think I must say. And that is why it will draw current. And if it draws current, you have to treat it just like a resistor. So if you treat it just like a resistor, okay, the net resistance of this combination would be parallel combination of 10,000 ohms. Yes, 10,000 ohm with 400 ohms and 800 ohm in series. So I can say the total current going in this circuit is 6 divided by net resistance. Let's write net resistance, RV times 400 divided by RV plus 400. This is the net of these two, plus 800 plus 800. This is the current. Okay. If you multiply this current by 800 ohms, you will get potential across this 800 ohm. because the current is splitting here, but it is recombining here. So in 800 ohm, the voltage is I times 800. And if you subtract this value from 6, because across this the voltage is 6, here we have voltage by this value. So total voltage minus this voltage will give you voltage across this combination, means potentiometer. So this is your final answer and reading of voltmeter. Okay, and after calculating this, put the value of RV as 10,000 and you will get nearly as 1.95 volt. So correct answer is C. Okay, bachcho. Next, move to next. Again, it's a very simple question, and it says in a circuit to verify Ohm's law, we use ammeter and voltmeter. To verify Ohm's law, we use ammeter and voltmeter. Okay, voltmeter and ammeter reads simply the voltage across a resistance and current in that resistance. Okay, and by varying voltage and current in that resistance, and by proving every time the ratio of V upon I comes same, I can say the Ohm's law is verified. Okay, because Ohm's law says V is proportional to I. But if we have to do this, obviously you know the ammeter is connected in series and voltage in parallel. So ammeter should be connected in series and voltmeter in parallel. So obvious answer is A. Okay, so over to next question. So dear students, we learned ammeters measure current and voltmeters measure voltages or potential difference. But when we want to measure a resistance, the first method that comes to our mind is ammeter and voltmeter method. Because if you measure current in a resistance using ammeter and potential difference across that resistance using a voltmeter, you can simply divide V upon I, the reading of voltmeter and reading of ammeter, to get value of resistance. But since we do not have ideal voltmeters and ammeters in daily life, so it becomes very difficult to get correct value of resistance, since either the voltmeter will read false value or the current will read false value. So a direct and more accurate method of measuring a resistance is a meter bridge. Okay, a meter bridge. Why it is called a meter bridge? Because it has a specific wire of length 1 meter in it. So this is the specific wire of length 1 meter. This is a meter scale shown in the diagram. Okay, this specific wire is say has resistivity rho and cross section area A. One special thing about this wire is it has uniform resistivity and uniform cross section area over the length of 1 meter. Then we have two gaps in it. The left gap, in left gap we connect a standard resistance. The value of a standard resistance R is known, and in the right gap we usually put a unknown resistance. So this is the unknown resistance S and its value is to be found. Okay, the meter bridge, in meter bridge this wire is divided into two parts by this sliding contact D, and this sliding contact is connected to point B by a galvanometer. Okay, so can you see these two resistances act as two resistance of Wheatstone bridge, two upper resistances of Wheatstone bridge. These two parts of the 1 meter wire act as two lower resistances of meter bridge, and this galvanometer act as the diagonal resistance of meter bridge. Okay, so we have Wheatstone bridge. So we have a Wheatstone bridge like RS and this resistance and this resistance. So first what we do, we move this sliding contact over the length of the wire to get null point, and null point is obtained when there is no current in galvanometer. So when galvanometer pointer shows you zero deflection, now we know this is balanced, and if this is balanced, the ratio of these two resistances and ratio of these two resistances, these two resistances of these two parts will be same. So when we get balance, the ratio of these two resistances R divided by S equals the ratio of these two parts, the ratio of resistances of these two parts. So resistance of this length would become, as resistance is rho L upon A, resistivity is rho, length is X divided by area, divided by rho, the second part's length is 100 minus X divided by area, and as area and resistivity are uniform over the length, we can cancel them and we get the value of S as R times 100 minus X divided by X. So in balanced conditions, if you measure this length X using this meter scale, you put the value of X here, the R is already known. So by some calculations, the unknown resistance F can be measured far accurately than voltmeter and ammeter method. So this was the basic principle of meter bridge. Let us solve few previously asked questions based upon this. Okay. So in first question, what we are given, that we have a resistance wire and the resistance wire of length 1.5 meter is connected in the left gap of the meter bridge, and in the right gap we have a 10 ohm resistance. Okay. So you can take the help of this diagram. We have a resistance wire of length 1.5 meter in the left gap and a 10 ohm resistance in the right gap. Okay. And at balance point, the bridge wire is divided into the ratio 3:2. So the bridge wire is divided in the length ratio of 3:2. So what we can write is, okay, let the left gap wire or the resistance of resistance wire is R divided by right gap wire, which is right gap resistance is, I think, 10 ohm, yes, and the length ratio in which the sliding contact divides the main resistive wire is 3 divided by 2. So from here you know the resistance value is 15 ohm. Okay. Now they are asking what would be length of 1 ohm of the resistance wire. What will be length of 1 ohm? So as we know, the length of resistance wire is 1.5 meters and resistance of resistance wire is 15 ohm. We can use unitary method and I can say the 15 ohm resistance has a length of 1.5 meter. So 1 ohm resistance will have a length of 1.5 divided by 15 meters, that is 0.1 meter, and 0.1 meter. So if you check the options, you will see the C answer is correct. Okay, so let's move to next question. Here we have a question where they say, on interchanging the resistance, the balance point of a meter bridge shifts to the left by 10 centimeter. The resistance of their series combination is 1 kilo ohm. How much was the resistance on the left slot before interchanging the resistance? So let's take again the help of this diagram. Suppose on the left we have R and on the right we have S. Okay, and suppose the balance is obtained at a distance X from left end. Okay, R, S, distance X, and this is 100 minus X. So what we will have, according to balance conditions, we will get R divided by S equals X divided by 100 minus X. Now they say that if we interchange the resistances, if we interchange the resistance, means R on the right gap and S on the left gap, then we will have the ratio of S by R, and now at the balance, the sliding contact shifts by 10 centimeter towards left. So if sliding contact moves towards left, the X will be replaced by X minus 10, because in one length we will have to decrease one length by 10 centimeter and we will have to increase the other length by 10 centimeter. So the other length would be 110 minus X, right? Now let us solve these two, and for solving these two, let us simply multiply them. Okay, so when LHS is multiplied by LHS, we get R upon S multiplied by S by R, that is 1. and on the right hand side we will have x divided by 100 minus x times x minus 10 divided by 110 minus x. Okay. Let's calculate it. So, on multiplying and cross multiplying, we have 11,000 minus x square minus 100x minus 110x, that is minus 210x, equals to, on the right hand side, we have plus x square. On the right hand side we will be having x square minus 10x, that is x square minus 10x. So let's cancel x square by x square, and we have 200x on the right. So the value of x would be 11,000 divided by 200. That would be 55. Okay. So x is 55. And if x is 55, let us put this value in any one of them, r by s. So we have r by s equals 55 divided by 100 minus 55 is 45. So 55 divided by 45. Also they have said that sum of these two resistance is 1000 ohm. So let's put the value r plus s equals 1000. So I think now the calculations are very simple, and as you can see, r plus s is 1000, r by s is 55 by 45. So obviously the value of r should be 55, 550, and s should be 450. So the value of r with that, which is the left slot resistance before interchange, is r. So r's value is 55 into 10, that is 550. Okay. So here in this question they say the null point is obtained at a distance of 40 centimeter from A. So if this is 40, obviously this becomes 60, right? This is 40 and this is 60. And since null point is obtained, I can write R1 by R2 equals 40 by 60, that is 4 by 6 or 2 by 3. Okay. Now they say if I connect a 10 ohm resistance in series with R1, so R1 becomes 10 plus R1 and balance point shifts by 10 centimeter. So as you are increasing R1, the left slot resistance, this must increase. So it must increase, so it becomes 50, and it becomes 50, this also becomes 50. So at the place of R1 now comes R1 plus 10 divided by R2, and this becomes 50 by 50, that is 1. Okay. So now I know R1 plus 10 equals to 1. Okay. R1 plus 10 equals to R2. So R1 plus 10 equals R2, and R2 is 3 by 2 R1. Can you see that? R2 is 3 by 2 R1. So from here we know 1 by 2 R1 is 10. So R1 becomes 20 ohms. R1 is 20 ohm. But now with R1 a 10 ohm resistance is also connected. So in the left slot it becomes 30, right? Now they have said something new. If I connect another resistance, another unknown resistance in parallel with this R1 plus 10, means this 30, such that the balance point shifts to initial position, means by connecting some resistance X in parallel with R1 plus 10, that is 30 in parallel, so X plus 30, the balance point will shift to initial position, means the new resistance becomes equals to R1, which was initially there, and R1 is 20. So let us solve this for X, and now I have 3X minus 2XX, so X equals to 60 ohms. So correct answer is, I think, yes, C. Okay. So let's move to next question. Here, this is a very good question, and it says in meter bridge experiment, okay, the wire of length 1 meter has non-uniform cross section. Can you see that? Here the wire is thin and here wire is increases in thickness. The wire's thickness increases. Okay. The variation of dr by dl of the resistance R with length L is dr by dl is proportional to 1 by root L. Okay. Dr by dl is proportional to 1 by root L. And equal resistances are connected in these two slots. Okay. So if these two slots have equal resistance in them, the balance point will be obtained where these two parts will have equal resistance. Okay, will have equal resistance. So let us see. Next, they say the galvanometer has zero deflection when jockey is at a point P. At a point P means L distance from left end. When jockey is at this point P, the balance conditions are obtained. And if balance conditions are obtained, obviously this part's resistance should be equal to this part's resistance, as these two resistances are equal. Okay. So from here we know dr by dl is proportional to 1 by root L. I can write dr by dl equals to some constant, let us say k times k divided by root L. So I can write dr as k dl divided by root L. Now, according to conditions of problem, the resistance of this length is equal to resistance of this length. So let us integrate. As resistance of length from 0 to L is same as resistance of length from L to 1, I can put dr as k dl by root L. So it will be simply k outside the integration sign, and we have root L dl from 0 to L equals to L to 1 and k again common root L dl. As L's power is 1 by 2, sorry, it was in the denominator. So I should write L to the power minus 1 by 2, and here also L to the power minus 1 by 2. So after integration it becomes L to the power 1 by 2 divided by 1 by 2, that is this, from 0 to L, and because k got cancelled, and again 2 root L from L to 1. By opening this, we have 2 root L equals 2 also cancelled out. So root L equals 1 minus root L. Okay. So now bring this root L here and you will have 2 root L, square it. So 4L equals 1. So L equals 1 by 4. So L equals 1 by 4 means the value of L, what is the length? AP. So AP is the L and L becomes 0.25, that is 1 by 4. So correct answer is A. Okay. Let's move to next question. Now I have a meter bridge and S is a standard resistance. S is a constant standard resistance and R is a resistance wire. R is a resistance wire. Okay. And we found that balancing length is 25 centimeter. If balance length is at 25 centimeter, I can write R by S equals 25 divided by 100 minus 25, that is 75, that is 1 by 3. Now they say if R is replaced by a wire of half length and half diameter. So R is replaced by R dash and having the same material. So in R dash we have same resistivity as R, but half the length of R, and half the diameter. If diameter is halved, you know the cross section area is 1 by 4. Okay, cross section area is 1 by 4 because the area depends upon diameter square. So if you decrease the diameter by 1 by 2, the area, the next new area would be A by 4. So A by 4 goes up and you see 2 times of R. So the new resistance which is being replaced by which is replacing this resistance R is 2R. Okay, and now they are asking about the balancing length L dash. So if R is replaced by double resistance 2R, I'll say 2R divided by S should be equal to new balancing length L dash divided by 100 minus L dash. Okay, as the value of R by S is 1 by 3. Don't forget, R by S is 1 by 3. Put R by S is 1 by 3. We have 2 by 3 equals to L dash divided by 100 minus L dash. So here we have 200 minus 2L dash. On the right, send it to the right, we have 5L dash. So L dash equals 40 centimeter. So correct answer is 40 centimeter. Right? Let's move to next question. Again, it is a very simple question. They say consider a 72 centimeter long wire. Instead of a 1 meter long wire, they are taking now a 72 centimeter long wire. It doesn't make any difference. And they say these two resistances are 12 and 6, right? Okay, on AB at a distance x centimeter from A, at AB at a distance x centimeter from A, the balance conditions are obtained. Okay, the value of x should be. So just apply the balance conditions of meter bridge. So we have 12 divided by 6 equals to x divided by 72 minus x. Okay, so it becomes 144 minus 2x equals to x. So it becomes 144 equals to 3x. So x becomes 48 centimeter. So x is 48 centimeter and that is your answer. Okay, let's move. Now we have potentiometer. And this is very, very important for this chapter because you will have tons of questions in previous year papers. Okay. So what is a potentiometer? As the name suggests, potentiometer. Potential is from potential and meter is from measurement. So it is a device that measures potential difference, So it is used to measure potential difference. Okay. And the one very important feature is it can measure exact EMF of a cell. Why exact EMF of a cell? Measurement of exact EMF of a cell was difficult with voltmeter because whenever you connected a battery, a real battery with some internal resistance to a voltmeter, every practical or real voltmeter has some resistance. And if it has resistance, there would be some current going in it. And when current passes in this circuit, the terminal potential difference will be recorded as V equals to EMF minus IR. So we always have this error and the voltmeter reading will never be equal to EMF. So that is a theoretical error in measurement of EMF by voltmeter. But this theoretical error is completely removed in potentiometer. So let us see how. In potentiometer also we have a special wire AB and AB has got some resistance and it has got some length. Okay, the AB has length L, usually 100 meter, 200 meter or 10 meters, 100 centimeter, 200 centimeter or 5-6 meters also, and AB has length and resistance also. The AB is given supply by some accumulator EMF, let's say E naught. It is just a battery and some resistance R naught. It also has its own resistance R and length L. This circuit is called primary circuit. Okay. In the secondary circuit, we put the batteries whose EMF is to be measured. So in secondary circuit, we may have a single battery, we may have multiple batteries, or we may have a parallel combination of battery and resistance depending upon its applications. So here I have taken two batteries E1 and E2 and suppose their EMF, their exact EMFs are to be compared. Everything should be connected with a switch so that anytime you can remove them from circuit. So these are the switches, let's say S1 and S2. Okay. One very important thing is the polarities of primary circuit and secondary circuit should match. So if primary circuit is positive at the left, the secondary circuit too as a whole must be positive towards left. Only then the balance conditions would be obtained. Okay. One very important thing. Again, here also we look for null point. So we move this sliding contact on this wire, and where the position where we get null point, we stop the wire, and let's say we have the null point at a distance x from A. If we have a null point at a distance x from A, null point means there in galvanometer there will be no current. So here we will have no current, I is 0. Okay. And see, if in this secondary circuit is connected to primary circuit by two wires, one this galvanometer wire and one this wire. So if there is no current in this wire, there will be no current in this wire also. No current. So if here we have no current, here we have no current, I can say electrically these two circuits are not interacting. They are isolated from each other, and if they are isolated from each other, we can solve them separately. So what is the main equation that we use in every question? There is only one equation. This point is A, let's say this point is J. Okay. So obviously in null conditions, the potential difference across AJ, will be same as potential difference across secondary circuit, right? Suppose this point is P and Q. The important equation that solves every problem is potential difference across AJ equals potential difference across PQ. Okay. So how to solve potential difference across AJ? We will have to perform two steps in every problem. So step 1 would be finding potential difference across AJ. Step 1. If in some problem they give you potential difference on unit length of this wire, okay. If potential difference per unit length of the wire is represented by dV by dx, dV by dx is potential difference per unit length of the wire, or potential drop per unit length of the wire, or potential gradient. It is also called potential gradient. If this is given, if eta is given, eta is the, simply repeat eta, eta is potential drop on wire AB per unit length of the wire. So if you know per unit length potential drop, delta V across AJ in null conditions would be given by potential drop per unit length multiplied by length x, and this is the potential difference across AJ. Okay, this is the one method. The other method can be, if in some problem they give you the value of this EMF, they give you numerical value of this resistance, they give you numerical value of this resistance R, the current in primary circuit can be found as current in primary circuit, let's say I equals EMF E naught divided by R plus R naught. Okay, so delta V across AJ can also be found as the current in this wire, and resistance of this wire AJ, current multiplied by resistance of this wire AJ. Okay, so let's find current multiplied by resistance of AJ. What is current? Current is E naught divided by R plus R naught, and resistance of AJ. How to write resistance of AJ? You know the resistance of whole wire AB is R, so resistance per unit length is R by L, as the length AB is L. So resistance per unit length is R by L, So resistance of X length would be R by L into X. So this is the way we find potential difference across AJ. Okay, potential difference across AJ. So in step 1, you have to take either of the two methods. If it is a theoretical question, just assume some potential gradient and delta V AJ will be potential gradient times balancing length. Okay. If they give you numerically all the values of primary circuit elements, then find current in primary circuit and then multiply it by resistance of AJ. And this is how you find potential difference across AJ. Step 2. Step 2 is finding potential difference across PQ. So finding potential difference across PQ is not that difficult. Every time you will see PQ. PQ is a simple circuit, and by using KVL or KCL you can easily find the potential difference across PQ. Okay. So how to perform this experiment where we have to compare the EMFs of these two batteries? Okay. Let's talk about this experiment. By KVL. Okay. To compare EMFs. If you have to compare the EMFs of two cells, first what you should do, you should close this S1 only, and if you close this S1 and look for balancing point, and suppose if you close S1, balance point is obtained at X1. S1, S2 and value of X balance point. Open, close. Suppose S1 is closed, S1, S2 is open, means only first battery is in the circuit. Okay, and now you get balance point as S1 is open. Sorry, S1 is closed actually. S1 is closed. I should write in this way: S1 closed, S2 open. And now balance conditions are at say X1. Now you open S1 and close S2, and now say balance conditions are at X2. So according to your first condition, when let us see S1 is closed, okay, S2 open, means only one battery is here, and you obtained balance conditions at X1. So if you obtain balance conditions at X1, the delta VAJ can be written as potential gradient times X1. Okay. And what about delta V PQ? See, here we have no current, here we have no current, here we have no current. So if look at this point, if we have no current in this line, if we have no current in this line too, we will be having no current. No current here, no current here. According to KCL, we will be having no current here. So across this resistance R1, there will be no potential drop. And if in this resistance there is no potential drop, this is closed. So potential difference across PQ would be equal to only E1, because there is no potential drop in the internal resistance R1 because current is absent. Okay. So we get delta V PQ as E, and as we have to make delta V AJ and delta V PQ equal, I can say it is equal to E1, right? Similarly, you can say when S2 is closed, S1 is opened, the first battery is removed from the circuit, only second battery is in the circuit. Now the balance points, this is X1 actually, the balance point is obtained at X2. So delta V AJ becomes eta times X2, and obviously the potential difference across secondary circuit would become equal to E2. And since x1 and x2 are known, the E1 divided by E2 becomes x1 divided by x2. By measuring the two null point lengths, you can compare E1 upon E2, means the EMFs are now compared. There is one more very interesting experiment of finding EMF of a battery and its internal resistance. What we need additionally, we need a potentiometer setup, and we also know a known resistance R. So suppose we know the EMF of this battery as E naught, this resistance is R naught, this resistance is R, means the wire resistance is R and the length is L. Okay. For first, what we first do, we make S1 closed. So S1 closed. If S1 is closed, and look for null point, and say null point is obtained at x1. We found at x1 null point is obtained by moving the sliding contact. Suppose the null point is obtained at x1. Okay. If null point is obtained, the primary circuit and the secondary circuit are isolated from each other. And if they are isolated from each other, the potential difference across AJ should be same as potential difference across PQ. Okay, potential difference across AJ, delta V AJ, can be found from multiplying current in the primary circuit by resistance of this wire. As I discussed, the current in the primary circuit would be E naught divided by R plus R naught, multiplied by resistance of wire AJ should be R by L times X1. This is delta V AJ. And delta V PQ, as this is open, it has no meaning, it is meaningless. Across PQ, since current is absent, and if current is absent in this circuit, delta V PQ, potential difference across PQ, would be simply be E1. So delta V AJ equals to E1. So your E1's value is E naught divided by R plus R naught, R by L, X1. So by measuring X1, X1, you know the value E1. What is this actually? This is actually potential gradient. You can also call it eta, and eta is now known because everything in this problem would be known. Okay. Now you close S1 and S2 both. S1 and S2 both closed. If S1 and S2 both are closed and null point is found at X2, now you can say delta V AJ would be equal to eta. This is eta actually. This whole thing is eta and times X2. X2 is known because you have measured X2. Eta is already known. You know this value. Okay. So delta V AJ is known, and we have to find delta V PQ. Delta V PQ. Let us see how to find delta V PQ. We do not have any current here. But we do have a current here because this is also closed. So we do have a current here. And if we do have a current here, you can say delta V PQ would be the potential difference across this resistance R. And potential difference across this resistance R would be current in this loop multiplied by R. Can you see current? What is the current in this loop? The current in this loop would be E1 divided by R1 plus R. This is the current, and multiplied by R. This is the potential difference across R. Now you make these two things equal, delta V AJ and delta V PQ. If you make delta V AJ and delta V PQ equal, you will get E1 divided by R1 plus R times R equals eta X2. X2 you have measured, eta you already know, E1 you already know because of this equation, E1 you already know, equation 1. Okay, so now R is the standard and predefined resistance that you already know. This will be given in the question, so R1 can be calculated. Okay, so that is the basic principle of a potentiometer. In potentiometer, at null point conditions, potential difference across AJ and potential difference across PQ is same. So just find the potential difference across AJ, find the potential difference across PQ and equate them, and that will solve all your problems. Okay, so let's see some of the problems asked in previous years. In first question, we have a potentiometer wire 100 centimeter long, right, and constant potential difference is maintained across it. Two cells are connected in series first. Okay, so actually in secondary circuit, two cells, let's say this is the potentiometer wire and we have a constant potential difference across the wire maintained. Okay, so let us suppose the potential gradient on this wire dV by dx on the wire is eta. This is the potential gradient. Now you have connected two cells in series and they say two cells are connected in series first to support one another, means the polarities are same and then in opposite direction. So first they are connected to support each other and the balance point are obtained at 50 centimeter and 10 centimeter. So when they are supporting each other, the balance point is obtained at 50 centimeter. If they are supporting each other in null point conditions, potential difference across secondary circuit would be E1 plus E2 as they are supporting each other. Okay, so EMF will be this and that will be equal to eta times 50 because the first balance length is 50. At second case, when they are opposing each other, means their polarities are opposite, the net EMF should be E1 minus E2 and now the null point is obtained at 10 centimeter from the positive end, means eta times we have 10. Now if we divide these two, you will have E1 plus E2 divided by E1 minus E2 equals 50 by 1, that is 5. Use componendo and dividendo and you will have E1 upon E2 as 6 by 4. 5 plus 1 upon 5 minus 1, that is 6 by 4 and 6 by 4 is actually 3 by 2. So their ratio is 3 by 2. Okay, so that is the very simple question based on potentiometer. Let's see for next. Okay, here they are asking a potentiometer is an accurate and more versatile device than voltmeter to make electrical measurement of EMF because the method involves. Okay, because the method involves. You know why voltmeters were unsuccessful? Because when you have connected voltmeter, they used to read terminal potential difference. And terminal potential difference equals E minus IR. And there is always some current when you have applied a real voltmeter across a battery. There is always some current. And because of this current, this is the error in measurement. Okay. But when we use potentiometer, in null point conditions, there is no current through the battery. And if there is no current through the battery, obviously the potential difference across the battery and EMF is same. So that is the main cause that a condition of no current flows through the galvanometer or battery. This is the main cause a potentiometer is more successful, a more versatile, more accurate device than voltmeter. So correct answer is C. Next question. Now we have another a potentiometer circuit with a cell of EMF 1.5 volt, give balance point at 36 centimeter length of the wire. Okay, obviously if we have 1.5 volt EMF and it gives balance at 36 centimeter, means 1.5 equals potential gradient times 36 centimeter. And another cell of EMF 2.5 volt, 2.5 volt replaces the first cell. Then at what length of the wire the balance point occurs? Let's say this time the balance point occurs at length x. So just making the potential difference across AJ and potential difference across secondary circuit equal, you have these two equations, just divide them and you will see x divided by 36 equals 5 divided by 3. So x equals, I think, 60 centimeter. Yes, and the correct answer is A. Okay, correct answer is A. So let's move for a few more questions. Again, in a potentiometer experiment, it is found that no current passes through galvanometer when terminals of cell are connected across 52 centimeter, means balance point is across 52 centimeter of the length of the wire. Okay. If cell is shunted by a resistance of 5 ohm, let us see what they are saying. They are saying if you use only a cell of EMF E, the balance point is obtained at 52 centimeter of potentiometer wire. Okay, so let us say the potential gradient is eta and the length is 52. So this is the first condition. Now if I shunt the cell by a resistance of 5 ohm, a balance is found when cell is connected across 40 centimeter of the wire. Okay, so when you this question is actually this type. When we were using only cell, when we were using only cell, means this switch was open and balance point was obtained at 52 centimeter. So I can write EMF equals to eta times 52. But when we shunt this cell with a resistance, we shunt with this cell with a resistance, a current flows in it, and then the potential difference across PQ can be found by multiplying current in this loop and resistance of this wire. Okay, so let us draw this in our question. Yes, the question is like this. Initially we had only one cell and its resistance, and it was giving null point at 52. That's why we wrote this equation. But when this cell is shunted by a 5 ohm resistance, balance point is again obtained at 40 centimeter, but in this loop there must be some current. So for finding potential difference across these two, let us find current here, and the current would be E divided by 5 plus R. Okay, this is the current, and if you multiply this current by 5 ohm, you get potential difference across this and make this potential difference equal to eta times 40. Okay, and now if you divide these two equations, let us divide them, and what you get, I think you get 5 plus R divided by 5 equals 52 by 40. Okay, 52 by 40. Let us further solve it. Yes, we have 2R equals 13 minus 10, 3. So R equals 1.5 ohms. So internal resistance is 1.5 ohms. Okay, students, let's move for next question. Okay, again the questions are simple, but just you have to remember is you have to make in every question potential difference across AJ equals potential difference across secondary circuit, and potential difference across secondary circuit, and this thing you have to do in null point conditions. Okay, so here we have again a potentiometer wire AB of length L and resistance 12R. Its length is L and resistance is 12R. Here we have a battery of EMF E and internal resistance R. Okay, so we are given exact values of primary circuit. Okay. Now, in secondary circuit, we are connecting an EMF of E by 3 or epsilon by 2, sorry, E by 2 and internal resistance 3R. Then they are asking what is the length AJ at which galvanometer as shown in the figure will show no deflection. So suppose at a distance x the galvanometer is showing no deflection. If it is showing no deflection for this length, potential difference across AJ can be written as current in this primary circuit multiplied by resistance of wire AJ. We have learned, so let us write it again. The current in primary circuit would be E divided by 12R plus R, that is 13R. This is current in primary circuit multiplied by resistance AJ. The resistance AJ can be written as the total resistance. Total resistance was 12R divided by length L multiplied by X. So this is the current in primary circuit and this is the resistance of wire AJ. So this is the potential difference across AJ, and the potential difference across the secondary circuit in null point conditions should be E by 2 only. So make it equal to E by 2 only, and I think you will have R cancelled, E cancelled, and X becomes 13L by 24. So correct answer is D. Okay, next question. Now we have an ideal battery of 4 volt and resistance R, ideal battery of 4V and resistance R connected in series in primary circuit of a potentiometer of length 1 meter and resistance 5 ohm. So we have a wire 1 meter length, 5 ohm resistance and a 4 volt battery and resistance R. This is the primary circuit of the potentiometer. The value of R to give a potential difference of 5 millivolt across 10 centimeter of potentiometer wire. Okay, so actually we are getting 5 millivolt in 10 centimeter of potentiometer wire. Okay, actually if we are getting 5 millivolt in 10 centimeter, obviously we must get 50 millivolt in 100 centimeter, that is 1 meter. So across this wire you will get 50 millivolt. Okay, 50 millivolt. So how to find 50 millivolt? Actually 50 millivolt will be equal to resistance 5 ohm. So it is equal to basically potential difference across 5 ohm, and potential difference across 5 ohm would be current 4 divided by R plus 5 into 5. Okay, so let's solve it. I have 50 equals 4000 multiplied by 5 divided by R plus 5. Cancel this 50 and you have R as 400 minus 5, that is 395 ohms, and the correct answer is A. Okay, so let's move a little. Yes, now we have balancing length of a cell is 560 in a potentiometer experiment, and when external resistance of 10 ohm is connected in parallel to the cell, the balance length changes by 60 centimeter. It is again a similar question like this. Initially when we had only one cell, the balance length was 560, but when we have connected a cell in parallel, the balance length reduces by 60 centimeter. So yes, suppose we have EMF E as in secondary circuit and the balance length is 560. So let me write eta times 560. Okay. Now if 10 ohm resistance is connected in parallel to the cell, the balancing length changes by 60 centimeter. Internal resistance we have to found. So if 10 ohm is connected, the current in secondary circuit would be E by internal resistance plus 10 multiplied by 10. We will get potential difference across secondary, and this is equal to eta times 500 because 60 centimeter are reduced. Why only reduce? Actually you are reducing potential of secondary circuit. Can you see the new potential difference in secondary circuit is reduced? This factor is less than E. So if this is less than E, the balance length will also be reduced. Just divide these two and let's see what we get. We get R plus 10 divided by 10 as 56 divided by 50. So now you have R plus 10 as 56 by 5, and 56 by 5 is nearly 11.2. Yes. So R is equal to 1.2 ohm. Okay, but they are asking the internal resistance of cell is N by 10. So actually N by 10 equals 1.2. So the value of N will be 12. Okay, so let's move a little. Okay, in this question they say the E2 is 1.02 volt and the switch S is open and null point is obtained. Just think of it. Think of this junction. Here we have no current because S is open. Here we have no current because null point is obtained. So obviously we have no current here according to KCL. Okay, if we have no current here and if we have no current here, obviously here also we have no current. And here we have no current, here we have no current, so we have no current in E2 also. So this complex circuit is as simple as a common potentiometer circuit, and simply we have no current in E2. So balance point condition says the potential difference E2 should be equal to potential difference across P and J. So E2 equals eta times, eta means potential gradient, times the length, and length is actually 49 centimeter. Okay, so eta becomes 1.02 volt divided by 49 centimeter, which comes very close to 0.02 volt per centimeter. Okay, next question. Now the length of potentiometer wire is 1200 centimeter and it carries a current of 60 milliampere. So potentiometer wire, which is actually 12 meter long, is carrying a current also because of this some battery, and the current is 60 milliampere. Now a cell of EMF 5 volt and internal resistance of 20 ohm is connected and null point is found to be at 1000 centimeter. The resistance of whole wire is actually, okay. So we have a 5 volt cell here of internal resistance 20 ohm and we got null point at 1000 centimeter. Okay, we have null point at 1000 centimeter. Actually, if we have null point here, obviously there is no current, and if there is no current across this 20 ohm tube, there will be no potential difference. And if there is no potential difference here, you can say the potential difference in the secondary circuit is only 5 volt. So now you know the potential difference across this wire is also 5 volt. So if we calculate the potential difference of this wire of 1000 centimeter, it is simply 5 volt. So resistance of 1000 centimeter should be 5 divided by 60 milliampere, that is 1000. Okay, so that becomes 500 divided by 6 or 250 divided by 3. But remember, this is the length of 1000 centimeter, means 10 meters length. 10 meter wire has resistance of 250 by 3. Okay, so let's write unitary method. 10 meter wire has resistance 250 by 3. So 12 meter wire will have resistance equal to 250 by 3 multiplied by 10 into 12. Let us see what it comes. It is equal to 3 4s are 12. We have 100 ohm. So correct answer is 100 ohm. Okay. So let's move again for the next question, and it says potentiometer. In the next question says the potentiometer wire of length 100 centimeter has a resistance of 10 ohm. Okay. So we have a 100 centimeter wire, means 1 meter wire, and resistance of 10 ohm. Right. It is connected in series with a resistance and accumulator of EMF 2 volt. So we have a battery of 2 volt and a resistance, let's say R. Right. A source of EMF 10 millivolt is balanced against a length of 40 centimeter of the potentiometer wire. So we have a source of 10 millivolt and it is being balanced at a length 40 centimeter. Okay, at a length 40 centimeter. Okay. Then they are asking us what is the value of external resistance R. This R is to be found. Because of this balance, the potential difference, this is 10 millivolt actually. Okay. As 1 meter wire has a resistance of 10 ohm, the 40 centimeter will have a resistance of 4. Okay, so you can say this wire from here to here has a resistance of 4 ohm by unitary method. 100 centimeter resistance is 10 ohm, so 40 centimeter resistance is 4 ohm. And there is a potential difference across it, and what is that potential difference? 10 millivolt. So resistance of this part can be found from, let's say R1. R1 is 10 millivolt divided by current. Okay, current is I, but R1 is known. R1 is actually 4 ohm, so current is actually 10 by 4 milliampere. So now we know the current in the primary circuit. And if now I know the current in primary circuit can be written as the equation of primary circuit. Use equation of primary circuit as 2 divided by 10 plus R. 2 divided by 10 plus R. Okay. So let us see what it becomes. It becomes 10 by 4 equals 2000 divided by 10 plus R. Okay, 10 plus R. Cancel this 10. Okay, and now you see 10 plus R equals 800. So if 10 plus R equals 800, the R would be 790 ohms. So that was all about electric current, potentiometer, measurement of all electrical quantities. I wish you all the best for your exams. Thank you.